Space is the perfect hiding spot, right? Billions. And billions of kilometers of empty darkness. You would think hiding a spaceship there would be the easiest thing in the world. It turns out it's the exact opposite. And it's one of the hardest problems in engineering. In a vacuum, there are no clouds, fog, or mountains to hide behind. Any solid object stands out against the distant stars. But the biggest problem is heat. A spaceship, to keep people alive and computers running, generates a lot of heat. In the absolute cold of space, near negative 270 degrees. This heat shines like a beacon for any infrared camera. How do you hide a hot machine in the coldest place that exists? Prepare to fall asleep while listening to this video. Subscribe to the channel, leave your like, and comment what part of the world you are watching from. Get comfortable and relax. Let's begin. Have you ever wondered why we don't have invisible spaceships zooming around our solar system? It seems like it would be the perfect military advantage, right? Well, the reality is far more complicated than science fiction would have us believe. When it comes to hiding in space, we face a fundamental problem that makes stealth incredibly challenging. Space is often described as the perfect hiding place, vast, dark, and empty. However, this emptiness creates one of the greatest paradoxes for stealth technology. In the vacuum of space, there are virtually no natural elements that could help conceal a spacecraft. Think about hiding on Earth. You can use clouds, fog, mountains, or even the ocean depths to mask your presence. In space, none of these natural camouflage elements exist. The vacuum creates a crystal-clear environment where any solid object forms a distinct silhouette against the background of distant stars. This clarity is a fundamental obstacle to concealment. When you look up at the night sky and see satellites passing overhead, you're witnessing this principle in action. These objects are visible primarily because they block the light from stars behind them or reflect sunlight toward Earth. Another critical aspect of the vacuum problem is the lack of atmospheric scattering. On Earth, our atmosphere diffuses light in ways that can blur outlines and reduce visibility over distance. The famous blue haze you see when looking at distant mountains is an example of this phenomenon. In space, with no atmosphere to scatter light, optical sensors can detect objects with exceptional clarity even at enormous distances. The distances between objects in space might seem like they would help with concealment, but they actually work against it. Any movement that doesn't conform to natural orbital patterns immediately stands out to tracking systems. Spacecraft follow very predictable paths dictated by orbital mechanics, and any deviation requires thrust, which creates other detectable signatures we'll discuss shortly. The vacuum also means there's nothing to absorb or attenuate signals. Radar waves, for instance, travel unimpeded through space, bouncing off spacecraft and returning to detectors with minimal loss of energy. This creates an environment where detection ranges are vastly greater than in Earth's atmosphere. A radar system that might detect an aircraft at 100 kilometers on Earth could potentially spot a spacecraft at thousands or even tens of thousands of kilometers in space. This transparency also applies to electromagnetic emissions from the spacecraft itself. Any communication signals, radar systems, or even the electronic noise from onboard computers radiates outward in all directions with nothing to block or absorb it. Think of a spacecraft like a lighthouse in an ocean of darkness. Any emission becomes a beacon announcing its presence. Space agencies and military organizations have attempted various approaches to address this vacuum paradox. One method involves designing spacecraft with minimal cross-sectional profiles when viewed from certain angles. However, this only works if you know exactly where the observers are located, which is rarely the case in actual operations. Some have proposed using special coatings that absorb certain wavelengths of light or radar energy. While these can help reduce detectability in specific bands of the electromagnetic spectrum, they cannot solve the fundamental issue of the spacecraft blocking starlight. An observer with a powerful enough telescope can still see the hole in the star field where the spacecraft is located. The vacuum of space also creates challenges for any active camouflage systems. Theoretical technologies like screens that display images of the star field behind the spacecraft would need to be perfect from every possible viewing angle, a nearly impossible task given the three-dimensional nature of space and the vast number of potential observation points. Even the dust of space works against concealment. The interplanetary medium contains tiny dust particles that, when they impact a spacecraft, create minute flashes and disturbances. Over time, these impacts can be mapped to reveal the presence of an otherwise invisible object. Similarly, the solar wind, a stream of charged particles from the sun, interacts with any object in space, creating detectable disturbances in its flow pattern. The temperature differential between a spacecraft and the surrounding vacuum creates another significant challenge. In the shadow of Earth or other celestial bodies, space temperatures drop to near absolute zero, approximately negative 270 degrees Celsius. Any spacecraft with humans, electronics, or mechanical systems aboard will be significantly warmer than this background, creating a thermal contrast that infrared sensors can detect from extraordinary distances. Even nuclear-powered spacecraft designed to minimize external systems face the vacuum paradox. The heat from their power systems must eventually be radiated away, as there's no air or water in space to carry heat away through convection. These thermal emissions create distinctive signatures that stand out against the cold background of space. Perhaps the most insurmountable aspect of the vacuum paradox is that any effective stealth system would need to account for all possible detection methods simultaneously. A spacecraft might be designed to minimize radar reflection, but if it doesn't also address thermal emissions, optical visibility, and gravitational effects, it remains detectable through other means. This multifaceted challenge explains why, despite decades of advanced technological development, truly stealthy spacecraft remain in the realm of science fiction. The fundamental properties of the vacuum environment work against concealment in ways that are difficult to overcome with current or even theoretically advanced technology. Military strategists and spacecraft designers continue to develop technologies that reduce detectability in specific circumstances or against particular sensors. But the perfect stealth spacecraft, one that is completely invisible to all detection methods, remains an elusive goal primarily because of the unforgiving nature of the vacuum environment. The Thermal Signature Challenge. Did you know that hiding a spacecraft isn't just about making it look invisible? One of the biggest giveaways of any spacecraft lurking in the darkness of space isn't what you can see, it's what you can feel. Heat is perhaps the most persistent challenge in developing stealth technology for space operations, and it's far more complex than most people realize. Every operational spacecraft generates heat, substantial amounts of it. Life support systems keeping astronauts alive, computers managing flight operations, communication equipment transmitting data, and especially propulsion systems moving the craft through space, all produce thermal energy that must go somewhere. In the vacuum of space, this creates a fundamental problem for anyone trying to design a stealthy vessel. The temperature contrast between an operational spacecraft and the surrounding space environment is extreme. While a habitable spacecraft maintains interior temperatures around 20 degrees Celsius for human comfort, the background temperature of space hovers near negative 270 degrees Celsius. This creates a thermal difference of nearly 300 degrees, a beacon for modern infrared detection systems. Modern infrared sensors have reached astonishing levels of sensitivity. Military-grade systems can detect temperature differences of mere fractions of a degree from hundreds of kilometers away. In the crystal-clear vacuum of space, these detection ranges extend even further. Some of today's space-based infrared systems can identify the heat signature of a spacecraft from distances measured in thousands of kilometers or more. What makes this challenge particularly difficult is that heat doesn't just disappear when you turn systems off. The thermal mass of a spacecraft means that residual heat remains detectable for hours or even days after systems are powered down. A spacecraft can't simply go cold on demand to avoid detection. This persistent thermal signature means that even a dormant spacecraft leaves a detectable footprint in the infrared spectrum. Conventional approaches to thermal management actually compound the stealth problem. On Earth, engineers use insulation to keep heat in or out of a system. In space, insulation materials that prevent heat from escaping actually make the spacecraft hotter internally, eventually requiring even more heat rejection. These materials also tend to increase the physical size of the vessel, making it more visible to radar and optical detection systems. The fundamental challenge comes down to thermodynamics, specifically how to dispose of excess heat in an environment where convection and conduction are not available. On Earth, hot objects cool naturally as heat transfers to the surrounding air or water. In space, the only way to shed heat is through radiation, the emission of infrared energy directly from the surface of the spacecraft. This radiation requirement creates an inescapable signature. The laws of physics dictate that any object warmer than its surroundings will emit thermal radiation proportional to the fourth power of its temperature. This relationship, known as the Stefan-Boltzmann law, means that even slight temperature elevations above the space background create significant and detectable infrared emissions. Engineers have attempted various approaches to manage this thermal signature problem. One method involves directional heat management, concentrating heat rejection to specific areas of the spacecraft facing away from likely observation points. This approach requires precise knowledge of observer locations and perfect orientation control, making it impractical for most real-world scenarios. Another technique employs cryogenic cooling systems to reduce the external temperature of the spacecraft. However, these systems consume significant power and, ironically, generate additional heat that must also be managed. The energy required to power cooling systems creates a thermal management paradox. The more you try to cool the spacecraft, the more heat you ultimately generate. The human factor adds another layer of complexity to the thermal challenge. Each human body continuously generates approximately 100 watts of thermal energy simply by existing. A crewed spacecraft with several astronauts aboard has a baseline heat production that cannot be eliminated without eliminating the crew, clearly not a viable option for manned missions. Some theoretical designs have proposed storing heat temporarily within the spacecraft's thermal mass or in phase change materials that absorb heat as they melt. While these approaches can delay heat emission, they cannot eliminate it. Eventually, all accumulated heat must be rejected, creating periodic thermal signatures that sophisticated detection systems can identify and track. The materials science challenges are equally daunting. Creating surfaces that minimize thermal emissions requires specialized coatings with precisely engineered emissivity properties. These materials must maintain their performance despite exposure to micrometeoroid impacts, solar radiation, atomic oxygen, DOT, and other harsh space environment factors that cause degradation over time. Superconducting materials theoretically offer some promise for thermal management, as they can transfer heat with minimal energy loss. However, current superconducting materials require extremely low temperatures to function, creating yet another cooling burden. The weight, DOT, complexity, and power requirements of such systems make them impractical for all but the most specialized applications. Nuclear power systems, often favored for deep space missions due to their high energy density, present special thermal challenges for stealth operations. Radioisotope thermoelectric generators, RTGs, and nuclear reactors produce constant heat that cannot be switched off without abandoning the power source entirely. Their distinctive thermal signatures are particularly recognizable to surveillance systems designed specifically to monitor nuclear activities in space. Some military spacecraft designs have experimented with thermal metamaterials, artificially structured materials that can manipulate infrared radiation in unusual ways. These include directional emitters that concentrate heat radiation in specific directions and adaptive materials that change their emissive properties based on their temperature. While promising, these technologies remain in early development stages and face significant challenges in scaling to full-size spacecraft. The coming decades may see incremental improvements in thermal management for stealth spacecraft, but the fundamental physics of heat transfer in vacuum environments places hard limits on what's possible. Any object warmer than the background of space will emit infrared radiation that can be detected with sufficiently sensitive instruments. As detection technology continues to advance alongside stealth technology, the balance remains firmly tilted toward the observers rather than the hidden. This thermal signature challenge represents perhaps the most fundamental obstacle to creating truly stealthy spacecraft. While science fiction depicts invisible ships slipping silently through space, the reality remains that as long as spacecraft require energy to function, they will generate heat. And that heat will ultimately reveal their presence to those looking in the right spectrum. This thermal signature challenge becomes even more insurmountable when we consider the fundamental impossibility of complete cooling in space. Many science fiction enthusiasts might wonder, why not just cool the spacecraft to match the surrounding space temperature? The answer reveals yet another layer of complexity in spacecraft stealth design. Cooling a spacecraft to match the background temperature of space, roughly -270 degrees Celsius, is essentially impossible while maintaining a functional vessel, particularly one with a human crew. Human biology itself presents an insurmountable obstacle. Each person aboard a spacecraft generates approximately 100 watts of heat continuously through basic metabolic processes. This is roughly equivalent to having a 100-watt light bulb that never turns off for each crew member. This metabolic heat creates a constant thermal radiation source that cannot be eliminated without eliminating the crew. Even unmanned spacecraft face similar thermal challenges. Electronic systems, including computers, communication equipment, and sensors, generate heat during operation. Modern computing systems are becoming more efficient, but the complex calculations required for spacecraft operations still produce significant thermal output. The more sophisticated the spacecraft's capabilities, the more computing power it requires, and consequently, the more heat it generates. Some engineers have proposed advanced cryogenic cooling systems as a potential solution. These systems use liquefied gases at extremely low temperatures to absorb heat from the spacecraft. However, these create their own set of problems. The energy required to power cryogenic cooling systems is substantial, and ironically, this power generation itself produces additional heat. The more you try to cool the spacecraft, the more power you need, and the more total heat the system ultimately generates. This creates a paradoxical situation where perfect cooling becomes thermodynamically impossible. The physics of heat transfer in space compounds this problem. On Earth, objects can lose heat through three mechanisms: conduction, direct contact; convection, transfer via fluids like air or water; and radiation, emission of electromagnetic waves. In the vacuum of space, only radiation remains available. This makes heat dissipation extraordinarily inefficient compared to terrestrial environments. A spacecraft can't simply conduct heat away into surrounding matter or use convection currents to carry heat away. It must radiate all excess heat. Radiation heat transfer follows the Stefan Boltzmann law, which states that energy emission increases with the fourth power of temperature. This means that as an object gets closer to the background temperature of space, its ability to radiate heat away decreases dramatically. The final few degrees of cooling become exponentially more difficult to achieve, creating a practical lower limit well above the background temperature of space. Material limitations create additional barriers, superconducting materials, which could theoretically move heat with near-perfect efficiency. require extremely low temperatures to function, typically near absolute zero. These materials aren't currently viable for large-scale spacecraft applications due to weight considerations, fragility issues, and the enormous energy required to keep them cold enough to function. The structural materials needed to build a spacecraft also have minimum operating temperatures beyond which they become brittle and fail. Even the most advanced thermal insulation techniques face limitations in space. Multi-layer insulation, MLI, blankets can slow heat transfer but cannot eliminate it completely. Any insulation system must also include radiators to eventually release accumulated heat. And these radiators become obvious thermal signatures when observed with infrared sensors. The laws of thermodynamics create perhaps the most fundamental barrier to perfect cooling. The second law of thermodynamics dictates that entropy in a closed system always increases over time. In practical terms, this means that the energy used by cooling systems will always produce more total heat than they can remove. Perfect cooling would require a perpetual motion machine, something that violates the fundamental laws of physics. Some theoretical designs have proposed heat sinks that could temporarily store thermal energy during critical mission phases. These might use phase change materials that absorb heat as they melt from solid to liquid states. However, these systems can only delay heat emission, not eliminate it. Eventually, all stored heat must be radiated away, creating periodic thermal signatures that sophisticated detection systems can identify and track. The time factor also works against stealth operations. The longer a mission continues, the more heat accumulates within the spacecraft. Short-duration missions might manage their thermal signature for brief periods, but longer missions face compounding challenges as heat builds up within the system. Long-term stealth operations would require perfect thermal management indefinitely, something that remains beyond our technological capabilities. These fundamental limitations mean that even with our most advanced technologies, spacecraft will always operate at temperatures significantly above the background temperature of space. This temperature differential creates an infrared signature that, with sufficiently sensitive sensors, can be detected at enormous distances. As detection technology continues to advance alongside stealth technology, the advantage remains firmly with those doing the observing rather than those trying to hide. Beyond the thermal challenge, spacecraft face another equally difficult stealth hurdle, the problem of inevitable electromagnetic radiation. This challenge represents a different but equally fundamental physics problem that makes true space stealth extraordinarily difficult to achieve. Every electronic system aboard a spacecraft generates electromagnetic fields as a byproduct of normal operation. These fields are particularly problematic for stealth because they can travel enormous distances through the vacuum of space without significant degradation. The electromagnetic spectrum includes everything from radio waves and microwaves to infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays, and spacecraft emit across multiple bands of this spectrum. Communication systems represent the most obvious source of electromagnetic emissions. Any spacecraft needs to communicate with its home base, other spacecraft, or ground stations. These communications typically use radio waves that propagate in all directions, creating a detectable signature far larger than the physical spacecraft itself. Military spacecraft might use directional, high-frequency, or encrypted communications to reduce detectability, but any transmission creates some level of detectable emission. Even when a spacecraft attempts to maintain radio silence by not actively transmitting, its electronic systems still generate electromagnetic fields. Computers, power distribution systems, sensor arrays, and life support equipment all produce low-level electromagnetic emissions that leak from the spacecraft. These emissions, called unintentional radiators in stealth terminology, are extraordinarily difficult to eliminate completely. Modern electronic warfare systems are designed specifically to detect these faint electromagnetic signatures. The most advanced sensors can identify specific types of equipment based solely on their electromagnetic emission patterns. A spacecraft's electronic signature becomes something like a fingerprint that can be detected, catalogued, and recognized by sufficiently sophisticated monitoring systems. The electromagnetic challenge is made worse by the near-perfect vacuum of space. On Earth, the atmosphere absorbs certain wavelengths of electromagnetic radiation, limiting detection ranges. Water vapor, in particular, absorbs microwave frequencies, and various atmospheric gases absorb other portions of the spectrum. In space, this natural shielding doesn't exist. Electromagnetic waves travel unimpeded through the vacuum, potentially detectable at distances measured in millions of kilometers with sufficiently sensitive equipment. The background electromagnetic environment of space also works against stealth operations near Earth. Our planet generates significant electromagnetic noise from both natural and artificial sources. This background noise can help mask a spacecraft's emissions. However, as a spacecraft moves farther from Earth, the background electromagnetic environment becomes incredibly quiet. Against this silent backdrop, even minor emissions stand out dramatically, similar to how a whisper might be inaudible on a busy street but perfectly clear in a silent library. Radar detection creates a particular challenge for spacecraft stealth. Modern space surveillance systems use powerful radar arrays to detect and track objects in orbit. These systems work by broadcasting radio waves that bounce off spacecraft and return to the detector. Even with radar absorbing materials similar to those used in stealth aircraft, spacecraft face significant challenges in reducing their radar cross-section from all possible viewing angles. The power systems that keep spacecraft operational create their own electromagnetic signatures. Nuclear power sources, like radioisotope thermoelectric generators, RTGs, or small reactors, emit distinctive patterns of radiation. Solar panels interact with the solar wind and create detectable disturbances in local electromagnetic fields. Battery systems generate electromagnetic fields during charging and discharging cycles. Even the most efficient power systems create some level of electromagnetic emission. Some theoretical designs have proposed Faraday cage principles to contain electromagnetic emissions within the spacecraft, by surrounding electronic systems with conductive materials that block electromagnetic radiation. These emissions could potentially be reduced. However, perfect electromagnetic containment is practically impossible. Cables, sensors, communication systems, and viewing ports all create potential leakage points where emissions can escape. The operational requirements of a spacecraft create an inescapable dilemma. A spacecraft must either maintain communications and remain detectable, or maintain silence and lose operational effectiveness. Military spacecraft might accept temporary communication blackouts for stealth purposes, but extended communication silence significantly reduces mission capability and creates safety risks for the crew or spacecraft. Advanced electronic warfare techniques like frequency hopping, burst transmission, and highly directional communications can reduce detectability somewhat. These methods minimize transmission time or focus emissions in specific directions to reduce the probability of detection. However, they cannot eliminate the fundamental requirement for electromagnetic communication or the unintentional emissions from onboard systems. The physics of electromagnetic propagation in space creates a fundamental asymmetry that favors detection over concealment. It takes far less energy to detect an electromagnetic emission than it does to generate it in the first place. This means that even low-power emissions from a spacecraft can be detected by receivers using significantly less power, often from much greater distances than the spacecraft's own sensors can reach. As detection technology continues to advance, this challenge only becomes more pronounced. Quantum sensors, artificial intelligence-enhanced signal processing, and distributed detection networks are all improving our ability to detect faint electromagnetic signals against the background of space. These technological developments consistently favor detection capabilities over stealth technologies. The combination of inevitable thermal signatures and electromagnetic emissions creates a multi-spectrum detection problem that makes true spacecraft stealth extraordinarily difficult to achieve. While military spacecraft designers continue to develop technologies that reduce detectability in specific scenarios or against particular sensors, the perfect stealth spacecraft, one that is completely invisible to all detection methods, remains beyond our current technological capabilities and may be fundamentally impossible given the laws of physics as we understand them. Given these challenges with thermal and electromagnetic signatures, spacecraft designers have turned to specialized absorbing materials as a potential solution for reducing detectability. These materials represent some of our most advanced stealth technologies, but they face unique challenges when applied to the space environment. Materials that absorb radar and other electromagnetic radiation have been a cornerstone of aircraft stealth technology since the 1970s. The famous F-117 Nighthawk and B-2 Spirit stealth aircraft rely heavily on radar-absorbing materials RAMS to reduce their radar cross-section. These materials work by converting radar energy into heat through various mechanisms including magnetic and dielectric losses. When radar waves strike these materials, instead of reflecting back to the radar receiver, much of the energy is absorbed and converted to a tiny amount of heat. However, the effectiveness of these materials changes dramatically when used in space. The absence of atmosphere fundamentally alters how electromagnetic waves interact with surfaces. Materials that perform excellently in Earth's atmosphere may have significantly reduced effectiveness in the vacuum of space. The extreme temperature variations in space, from hundreds of degrees positive in direct sunlight to hundreds of degrees negative in shadow, also affect the molecular structure and performance of these absorbing materials. Weight considerations create another significant challenge for spacecraft stealth. Current radar-absorbing materials are notoriously heavy, with some specialized coatings adding significant mass to the structures they protect. This additional weight directly increases fuel requirements for space launches and orbital maneuvers. The rocket equation, which describes how much propellant is needed to move mass in space, is exponential, meaning that small increases in spacecraft weight require disproportionately large increases in fuel. This creates a vicious cycle. Heavier stealth materials require more fuel, which generates more heat, which makes thermal signature management even more difficult. The contradiction between different stealth requirements creates another engineering challenge. Materials that effectively absorb radar often have poor thermal characteristics. A coating designed to minimize radar reflection might actually make thermal management worse by preventing efficient heat radiation. This creates an impossible trade-off where designers must choose which detection method they want to counter, knowing they're likely making the spacecraft more visible to other detection systems in the process. Space is also an incredibly harsh environment for materials. The constant bombardment of solar radiation, particularly ultraviolet light, causes many materials to degrade over time. This degradation is accelerated in the vacuum of space, where there's no atmosphere to filter out harmful radiation. Materials that work perfectly when first deployed may become increasingly less effective over a mission's duration. Micrometeoroids, tiny particles moving at extremely high velocities, constantly impact spacecraft surfaces, gradually eroding protective coatings and changing their electromagnetic properties. The ideal absorbing material would need to work across the entire electromagnetic spectrum, from radio and radar frequencies through microwave, or infrared, visible light, ultraviolet, dot, and beyond. Creating such a broadband absorber remains one of the most challenging problems in materials science. Most current materials are optimized for specific frequency ranges, leaving spacecraft vulnerable to detection in other portions of the spectrum. Advanced research into metamaterials, artificially structured materials with properties not found in nature, offers some promise for space stealth applications. These materials can be designed to manipulate electromagnetic waves in highly specific ways. Some experimental metamaterials can bend light around objects, theoretically making them invisible to certain wavelengths. However, These technologies remain largely in laboratory settings, with practical applications limited by manufacturing challenges, durability concerns, and narrow operational bandwidths. Carbon-based materials like carbon nanotubes and graphene show potential for space stealth applications due to their excellent electromagnetic absorption properties and relatively low weight. These materials can be engineered at the molecular level to interact with specific wavelengths of electromagnetic radiation. However, mass production of these advanced carbon structures with consistent properties remains challenging, and their long-term durability in the space environment is still being evaluated. Some of the most promising research involves adaptive or smart materials that can change their absorption properties based on external conditions. These materials might use electrical stimulation to alter their molecular structure, allowing them to optimize for different threats or environmental conditions. However, these systems require power to function, creating additional heat and electromagnetic signatures that partially defeat their purpose. The economics of space stealth materials creates practical limitations as well. The most effective absorbing materials are often extraordinarily expensive, with some specialized coatings costing thousands of dollars per square meter. This expense makes covering large spacecraft surfaces financially prohibitive for all but the most critical military applications. The cost-benefit analysis rarely favors applying the most advanced materials to entire spacecraft, leading to partial solutions that determined observers can still detect. Despite these challenges, military and intelligence agencies continue to invest heavily in developing better absorbing materials for space applications. These research programs are among the most classified technological efforts, with advances rarely published in open scientific literature. The strategic advantage offered by even partially effective stealth capabilities in space drives continued research despite the seemingly insurmountable physical challenges. The reality of current absorbing material technology falls significantly short of what science fiction portrays. Rather than making spacecraft completely invisible, the best materials available today might reduce detection ranges or make identification more difficult under specific circumstances. Complete invisibility across all detection methods remains beyond our current technological capabilities, largely due to the fundamental laws of physics that govern how energy interacts with matter in the space environment. Even if perfect absorbing materials could be developed, spacecraft would still face another fundamental challenge that makes true stealth nearly impossible: the problem of detectable propulsion. Movement in space requires thrust, and generating thrust creates multiple signatures that reveal a spacecraft's presence regardless of how well its surface might absorb or redirect electromagnetic radiation. Conventional rocket engines produce perhaps the most obvious and detectable signatures of any spacecraft system. Chemical rockets work by expelling superheated exhaust gases at high velocity. This exhaust plume is extremely hot, often thousands of degrees, creating an intense thermal signature visible to infrared sensors across enormous distances. The brightness of rocket exhaust against the cold background of space makes active propulsion virtually impossible to hide. Military satellites specifically designed to detect missile launches can spot rocket plumes from thousands of kilometers away, making any significant propulsive maneuver immediately obvious to global monitoring systems. The visible light produced by conventional rockets is equally problematic for stealth operations. The combustion process creates a bright, distinctive flame that can be seen by optical sensors and even the naked human eye at considerable distances. This visible signature is particularly problematic during night operations when the contrast between the rocket flame and the dark background of space is most pronounced. More advanced propulsion systems face similar stealth challenges. Ion thrusters, which use electrical fields to accelerate charged particles, produce less thrust but operate much more efficiently than chemical rockets. While they don't create the intense thermal and visible signatures of chemical rockets, they generate their own distinctive signatures. The stream of ionized particles creates a detectable plume that interacts with the space environment in ways that sophisticated sensors can identify. The high voltages required to operate these systems also produce electromagnetic emissions that can be detected at significant distances. Nuclear propulsion systems, though offering tremendous advantages for deep space missions, present special detection challenges. Nuclear thermal rockets, which use nuclear reactions to heat propellant, produce radioactive exhaust that can be detected by specialized sensors designed to monitor nuclear activities in space. Nuclear electric propulsion creates distinctive electromagnetic fields from its power generation systems. The radiation shielding required for these systems also increases the spacecraft's radar cross-section, making it more visible to conventional detection methods. Solar sails and other propellantless propulsion concepts might seem promising for stealth applications since they don't expel hot gases or ionized particles. However, solar sails require enormous reflective surfaces to capture sufficient solar pressure for propulsion. These large, reflective surfaces act like mirrors in space, creating periodic flashes of reflected sunlight that can be seen across the solar system. The size and distinctive shape of solar sails also makes them easily identifiable in telescopic observations. The fundamental physics of orbital mechanics creates another propulsion-related stealth challenge. Objects in orbit follow very predictable paths dictated by gravitational forces. Any deviation from these natural orbital paths requires thrust, which creates detectable signatures. Sophisticated tracking systems can identify when a spacecraft's trajectory doesn't match expected orbital parameters, indicating that propulsion systems must be active even if the exhaust itself isn't directly observed. The energy requirements for significant orbital changes further compound the stealth problem. Moving between different orbits requires substantial energy and therefore substantial heat generation. The higher the energy maneuver, the more obvious the thermal signature becomes. Low-energy orbital adjustments might be somewhat less detectable but take considerably longer to execute, extending the period during which the spacecraft might be observed. Gravitational signatures represent another propulsion-related detection method that's difficult to counter. Any massive object in space creates a tiny gravitational field that influences nearby objects. While these effects are small, they can be measured with sufficient precision. A spacecraft maneuvering through a field of natural space debris or dust particles will cause subtle perturbations in their trajectories. Advanced observation networks monitoring these natural particles can potentially detect these gravitational anomalies, revealing the presence of an otherwise invisible spacecraft. The timing of propulsion activities creates strategic challenges for stealth operations. Spacecraft typically need to perform periodic station-keeping maneuvers to maintain their desired orbits. The longer a spacecraft operates, the more maneuvering it must perform, and each maneuver creates another opportunity for detection. This creates a fundamental operational limitation. Perfect stealth can only be maintained for limited durations before propulsion requirements compromise the spacecraft's hidden status. Theoretical, zero-signature propulsion concepts like space-time manipulation or gravity control remain firmly in the realm of science fiction. These concepts, while mathematically interesting, have no practical implementation with current or near-future technology. The physics of action and reaction, Newton's third law, dictates that propulsion requires expelling something or pushing against something, and these interactions create detectable signatures. Some military spacecraft designs have explored the concept of burst propulsion, using very brief, high-intensity thrust periods followed by long coasting phases. This approach attempts to minimize the time during which the spacecraft is actively emitting propulsion signatures. However, these high-intensity bursts actually create more noticeable signatures during their brief operation, and sophisticated monitoring systems need only catch a glimpse of such activity to begin tracking the object. The combination of these propulsion challenges with the previously discussed thermal, electromagnetic, and material limitations creates a multi-layered problem that makes true spacecraft stealth extraordinarily difficult to achieve. While military spacecraft designers continue developing technologies to reduce specific signatures under specific circumstances. The physics of propulsion fundamentally works against the concept of an undetectable spacecraft moving through space. Beyond the challenges of propulsion systems, spacecraft designers must contend with another fundamental obstacle to stealth, the problem of geometry and reflection. The very shape of a spacecraft creates distinctive patterns when illuminated by sunlight, radar, or other electromagnetic radiation, making it recognizable against the background of space regardless of what materials cover its surface. The physical geometry of spacecraft is typically dictated by practical requirements rather than stealth considerations. Launch vehicles have payload fairings with specific dimensions. Solar panels need maximum exposure to sunlight. Radiators must extend outward to efficiently dissipate heat. Antennas require specific orientations for optimal communication. These functional necessities create shapes that are distinctly artificial and immediately recognizable as non-natural objects when observed from nearly any angle. Reflection patterns represent one of the most significant geometry-related challenges. When sunlight strikes a spacecraft, it reflects in patterns determined by the spacecraft's surface geometry. Flat surfaces, which are common on spacecraft for structural and manufacturing simplicity, create specular reflections, mirror-like flashes that can be extraordinarily bright when viewed from certain angles. These reflections appear as sudden, intense points of light that stand out dramatically against the dark background of space, making them visible across enormous distances. Solar panels present a particular reflection challenge for spacecraft stealth. These large, flat surfaces are specifically designed to capture sunlight efficiently, which also makes them excellent reflectors when viewed from certain angles. Modern spacecraft often have large arrays of solar panels that can span dozens of meters when deployed. These create predictable, periodic flashes as the spacecraft rotates or changes position relative to the Sun and observer. Ground-based observers have spotted the International Space Station and other satellites primarily through these distinctive solar panel reflections. The problem becomes even more challenging when considering radar reflection. Radar systems work by sending out radio waves that bounce off objects and return to the receiver. Certain geometric arrangements like flat surfaces, right angles, and corner reflectors are particularly effective at returning radar energy directly to its source. Unfortunately, spacecraft design often requires precisely these geometric features for structural integrity and packaging efficiency. The result is that conventional spacecraft designs naturally have high radar cross-sections, the effective area that reflects radar energy back to the detector. Even attempts to reduce radar visibility through angled surfaces, similar to those used in stealth aircraft, face unique challenges in space. While aircraft stealth designs can be optimized for observers on the ground, spacecraft must consider potential observation from any direction in three-dimensional space. A shape optimized to reduce radar returns from one direction might actually increase visibility from another. This omnidirectional detection threat makes geometric stealth dramatically more complex for spacecraft than for atmospheric vehicles. Rotation creates another geometry-related challenge for spacecraft stealth. Many spacecraft rotate either for stability or to provide artificial gravity. This rotation creates rhythmic patterns of reflection as different surfaces move in and out of favorable reflection angles. These regular, predictable patterns are easily distinguishable from the random twinkle of stars or the steady light of planets. Advanced image processing algorithms can identify these characteristic patterns even when the spacecraft itself is too small to resolve as more than a point of light. The silhouette effect represents a particularly difficult geometric challenge to overcome. Even if a spacecraft could be made completely non-reflective, it would still block light from stars behind it, creating a moving hole in the star field that sophisticated observation systems can detect. This silhouette effect becomes more pronounced with larger spacecraft, unlike on Earth, where atmospheric haze and background complexity can help hide silhouettes. The crystal-clear vacuum of space makes even small silhouettes visible against the perfect backdrop of distant stars. Some designs have attempted to address these geometric challenges through dynamic shapeshifting. Theoretical morphing spacecraft could potentially change their physical configuration to minimize visibility from specific threat directions. However, these concepts face enormous engineering challenges related to structural integrity, weight, complexity, and the power required for shape transformation. The mechanical systems needed for significant shape changes would also create additional thermal and electromagnetic signatures that might defeat their stealth purpose. Surface texturing represents another approach to reducing geometric reflection problems. Rather than using smooth surfaces that create sharp, intense reflections, spacecraft could employ microscopically rough surfaces that scatter light in many directions, reducing the intensity in any one direction. However, these textured surfaces often interact poorly with the space environment, collecting dust, degrading under radiation exposure, and complicating thermal management. The manufacturing precision required for effective light scattering textures also adds significant cost to spacecraft construction. The distinctive geometric silhouettes of different spacecraft types create recognition challenges as well. Experienced observers can often identify specific spacecraft models simply from their characteristic shapes. Military intelligence agencies maintain extensive libraries of spacecraft silhouettes and reflection characteristics to aid in rapid identification. Even partial or degraded observations of a spacecraft's geometry can be sufficient for classification when compared against these libraries using modern pattern recognition algorithms. The most advanced stealth spacecraft concepts attempt to mimic natural objects in both shape and reflection characteristics. A stealth spacecraft might be designed to resemble a small asteroid, with irregular surfaces and rotation patterns similar to natural space objects. However, these designs face significant functional compromises. The irregular shapes that best mimic natural objects are often the worst choices for structural efficiency, internal volume utilization, and other practical spacecraft requirements. Some theoretical designs have proposed active camouflage systems that project images of the star field that would be visible behind the spacecraft. These systems would require precise knowledge of the observer's position and extremely sophisticated display technologies capable of mimicking the brightness, spectral characteristics, and apparent motion of background stars from multiple viewing angles simultaneously. The power, cooling, and computational requirements for such systems would be enormous, creating their own significant detection challenges. The combination of these geometric and reflection challenges with the previously discussed thermal, electromagnetic, propulsion, and material limitations creates a multi-layered problem that makes true spacecraft stealth extraordinarily difficult to achieve. While incremental improvements continue, the fundamental physics of how objects interact with electromagnetic radiation in the vacuum of space creates barriers that no current technology can fully overcome. Beyond conventional stealth approaches, some aerospace engineers and military planners have explored more exotic concepts like plasma stealth technology. In theory, surrounding a spacecraft with a controlled cloud of plasma, ionized gas, could potentially absorb or disrupt incoming radar waves and possibly mask other signatures. However, these plasma shield systems face their own set of nearly insurmountable challenges that have prevented their practical implementation. The basic concept behind plasma stealth is relatively straightforward in principle. Plasma contains free electrons that can interact with electromagnetic waves, absorbing or scattering them to prevent reflection back to radar receivers. By surrounding a spacecraft with a carefully controlled plasma field of specific density, radar waves might be absorbed before reaching the spacecraft's surface, effectively making it invisible to radar detection. Some research suggests plasma could also potentially mask certain infrared and other electromagnetic signatures. However, the energy requirements for creating and maintaining a plasma shield in space are enormous. Generating plasma requires ionizing gas atoms by stripping away electrons, which demands significant power. In Earth's atmosphere, where gas molecules are plentiful, Plasma generation is relatively straightforward, though still energy intensive. In the near vacuum of space, a plasma shield would require constantly replenishing the gas that forms the plasma, creating both a fuel storage problem and a detectable exhaust signature as gas escapes the ionization field. The power systems needed to sustain a plasma shield create their own major detection vulnerabilities. The energy required for large-scale plasma generation would likely necessitate nuclear power sources, which produce distinctive radiation and thermal signatures. Even with advanced power systems, the energy conversion inefficiencies would generate substantial waste heat. This heat would need to be dissipated, creating exactly the kind of thermal signature that stealth spacecraft aim to minimize. This creates a paradoxical situation where the system designed to enhance stealth actually makes the spacecraft more detectable in other portions of the electromagnetic spectrum. Containing plasma presents another significant technological hurdle. Without containment, plasma rapidly dissipates into space. The most effective method for plasma containment involves powerful magnetic fields, but these magnetic fields themselves become a significant detection signature. Advanced magnetometers can detect artificial magnetic fields at considerable distances, potentially making a spacecraft with magnetic plasma containment more detectable than one without plasma stealth at all. The interaction between these magnetic fields and natural space phenomena like the solar wind also creates detectable disturbances that sophisticated sensors can identify. Plasma also interacts unpredictably with the space environment. The solar wind, a stream of charged particles flowing outward from the sun, would distort and disrupt any plasma shield, creating visible patterns that don't occur naturally. These distortion patterns might actually make a plasma-shrouded spacecraft more noticeable than a conventional one. The interaction between a plasma shield and Earth's magnetosphere would create additional anomalies detectable by ground-based magnetometers and space-based sensors. The operational challenges of plasma stealth extend beyond physics and engineering problems. A plasma shield would interfere with the spacecraft's own sensors and communication systems, potentially blinding it to its surroundings while active. This creates a significant tactical disadvantage where the spacecraft must periodically deactivate its stealth system to observe its environment or communicate with its operators. These regular deactivation periods would create detection windows that sophisticated surveillance networks could exploit. Plasma shields would also potentially interact with space debris in dangerous ways. The high-energy plasma might alter the surface properties of small debris particles, affecting their trajectory through electrostatic forces. This could potentially increase collision risks rather than reducing them. The plasma might also accelerate the erosion of the spacecraft's own external surfaces, reducing mission lifetime and creating maintenance challenges. The technology required for effective plasma stealth remains decades beyond our current capabilities. The most advanced research in this area has primarily occurred in laboratory settings with small-scale demonstrations that cannot be readily scaled to operational spacecraft sizes. The physics of plasma behavior in space involves complex, often chaotic systems that are difficult to model accurately. Small-scale laboratory successes often fail to translate to real-world applications due to scaling laws and environmental factors not present in controlled experiments. Some nations have claimed breakthroughs in plasma stealth technology, particularly for atmospheric applications in advanced aircraft. However, independent verification of these claims is lacking, and the physics challenges for space applications remain significantly greater than for atmospheric use. The fundamental laws of thermodynamics, particularly regarding energy conversion efficiency and waste heat generation, apply regardless of the specific implementation details. The cost considerations of plasma stealth systems are equally prohibitive. The development, testing, and deployment of such complex systems would require investment potentially orders of magnitude greater than conventional spacecraft. The additional mass of plasma generation equipment, power systems, and containment mechanisms would dramatically increase launch costs. The reduced operational flexibility and increased maintenance requirements would further diminish the cost-effectiveness of such systems compared to alternative approaches. Despite these challenges, research into plasma stealth continues in classified military programs and advanced research institutions. The potential strategic advantage of truly stealthy spacecraft ensures ongoing interest despite the seemingly insurmountable technical challenges. Some researchers explore hybrid approaches that use plasma technology only for specific, limited stealth applications rather than complete spacecraft concealment. These might include plasma-based radar countermeasures or localized plasma fields to mask particular high-signature components. The reality of plasma stealth technology falls dramatically short of its portrayal in science fiction. Rather than creating perfect invisibility, current plasma technology might at best reduce certain signatures under specific circumstances and against particular detection systems. Complete stealth across all potential detection methods remains firmly beyond our technological horizon and may be fundamentally unattainable given the laws of physics as we understand them. The challenges of plasma stealth technology highlight a recurring theme in spacecraft stealth development. Apparent solutions often create new problems that can make the overall detection problem worse rather than better. This technological arms race between concealment and detection consistently favors detection due to fundamental physical principles that cannot be engineered away. This ongoing challenge between concealment and detection becomes even more complex when we consider the intricacies of spacecraft cooling systems. While we've touched on the thermal signature problem, the specific cooling technologies themselves create additional stealth complications that further stack the odds against truly hidden spacecraft. Conventional spacecraft employ radiators as their primary cooling mechanism. These radiators are essentially large panels designed to emit heat as infrared radiation. The problem is that effective radiators need to be large, often among the largest components of the entire spacecraft. The International Space Station, for example, has radiator panels spanning over 100 feet in length. These enormous structures create unmistakable visual and radar signatures that are impossible to conceal effectively. The very system designed to manage heat becomes one of the most visible aspects of the entire spacecraft. The size requirement for radiators comes from fundamental physics. The Stefan Boltzmann law dictates that the amount of heat a surface can radiate is proportional to its area and the fourth power of its temperature. To reject heat without becoming dangerously hot, spacecraft need large radiator surfaces. Attempts to make radiators smaller while maintaining cooling capacity inevitably result in higher operating temperatures, which ironically makes them more visible to infrared sensors. This creates a no-win situation. Either have large radiators that are visually obvious or smaller, hotter radiators that stand out dramatically in the infrared spectrum. Radiator orientation presents another cooling-related stealth challenge. For maximum efficiency, radiators need to point away from both the Sun and the Earth, or other nearby planets. This requirement creates predictable orientation patterns that distinguishing spacecraft from natural objects. Additionally, radiators must typically be articulated, able to change position to maintain optimal cooling as the spacecraft orbits. This movement creates distinctive patterns that automated detection systems can identify even when the spacecraft itself is too small to resolve clearly. Advanced spacecraft often employ cryogenic cooling systems for sensitive instruments and superconducting components. These systems use liquefied gases at extremely low temperatures, often just a few degrees above absolute zero, to absorb heat from critical components. However, these cryogenic systems require significant support infrastructure, including compressors, pumps, and specialized insulation. This equipment adds considerable mass to the spacecraft, increasing its radar cross-section and the power required for maneuvers. The cryogenic fluids themselves must also be stored in pressurized tanks that create additional detection signatures. The energy required to power cooling systems creates a vicious cycle for stealth design. Cooling systems typically consume 20 to 30% of a spacecraft's total power budget. Generating this power produces additional heat that must itself be dissipated. requiring more cooling capacity, which demands more power, and so on. This cycle means that cooling systems often create more total heat than they can effectively manage, with the excess becoming a beacon for infrared detection systems. Cooling system reliability presents strategic limitations as well. These complex mechanical systems represent potential single points of failure for the entire spacecraft. If cooling systems fail, temperatures quickly rise to levels that damage electronics and endanger crews. This vulnerability forces designers to include redundant cooling systems, further increasing the spacecraft's mass, power requirements, and detection signatures. The critical nature of these systems also means they cannot be temporarily disabled to reduce signatures during sensitive mission phases without risking catastrophic overheating. Superconducting materials offer theoretical advantages for thermal management, as they can transfer heat with near-zero energy loss. However, these materials only function at extremely low temperatures, typically requiring cooling with liquid helium at just 4 degrees above absolute zero. Maintaining these temperatures requires massive cryogenic support systems that generate their own heat and consume significant power. Current superconducting technologies remain impractical for large-scale spacecraft applications due to weight, complexity, and extreme sensitivity to even minor temperature fluctuations. Heat pipes, passive systems that use phase changes in working fluids to transfer heat efficiently, offer some advantages for spacecraft thermal management. However, these systems have limited capacity and typically serve to move heat from internal components to external radiators, rather than eliminating the need for radiators altogether. They also operate within narrow temperature ranges and can fail completely if their working fluid freezes or overheats. The orientation requirements for cooling systems create operational limitations that impact mission capabilities. A stealth spacecraft would need to carefully manage its orientation relative to potential observers to minimize the visibility of its cooling systems. This constraint severely limits maneuverability and can force mission planners to choose between effective cooling and reduced detectability, an impossible choice on longer missions where thermal management cannot be compromised without risking system failure. Thermal engineers have explored the concept of thermal camouflage, carefully controlling surface temperatures to match background radiation levels as viewed from specific threat directions. However, this approach requires perfect knowledge of observer positions and incredibly precise temperature control across the entire spacecraft surface. The power and computational requirements for such systems add yet another layer of complexity that ultimately generates more heat to manage. This approach also fails completely against multiple observers at different angles, a likely scenario in contested space environments. The cooling challenge highlights a fundamental limitation in spacecraft stealth design. The laws of thermodynamics cannot be engineered away. Heat must go somewhere, and in the vacuum of space, radiation is the only mechanism available. As detection technology continues to advance, with infrared sensors becoming more sensitive and more widely deployed in space-based surveillance networks, the thermal signatures from spacecraft cooling systems will become increasingly difficult to conceal regardless of technological advances. This cooling system challenge connects directly to another fundamental stealth problem, the paradox of radar invisibility. The very materials and techniques used to make spacecraft less visible to radar often create complications that make them more detectable through other means. This contradictory relationship represents one of the most frustrating challenges for stealth spacecraft designers. Radar-absorbing materials, RAMS, function by converting radar energy into heat. When radar waves strike these materials, rather than reflecting back to the radar receiver, the energy is absorbed and dissipated as thermal energy. This is the same principle used in stealth aircraft like the famous B-2 Spirit bomber. However, this conversion creates a significant problem for spacecraft stealth. The absorbed radar energy raises the temperature of the absorbing materials, increasing their infrared signature. A spacecraft designed to be invisible to radar might actually become more visible to infrared sensors precisely because of its radar-absorbing capability. The geometric requirements for radar stealth create another paradox. The most effective shapes for minimizing radar returns are angular, faceted designs with carefully calculated surface angles that deflect radar energy away from the receiver rather than back toward it. These distinctive geometric shapes, however, are immediately recognizable to visual and optical sensors as artificial, manufactured objects. Natural objects in space, asteroids, comets, and other debris typically have irregular, organically shaped surfaces. The angular geometry that best defeats radar makes the spacecraft more obviously artificial to visual observation. Most radar-absorbing materials are effective only against specific frequency ranges. Modern space surveillance networks employ multispectral radar systems that operate across many different frequencies simultaneously. A material designed to absorb X-band radar might be completely ineffective against L-band or K-band systems. Creating materials that work effectively across all potential radar frequencies dramatically increases weight, cost, and complexity. This frequency-specific performance means that even the most advanced stealth spacecraft remain vulnerable to sophisticated radar networks employing diverse frequency ranges. Another radar stealth paradox involves the spacecraft's own sensing needs. While a perfectly stealthy spacecraft would absorb all incoming radar without reflection, it would also need to operate its own radar systems to detect and track potential threats or mission targets. These active radar emissions immediately reveal the spacecraft's presence and location. This creates a functional contradiction where the spacecraft must either remain undetectable but effectively blind, or use its sensors and sacrifice its stealth capabilities. The need for communications antennas creates another inevitable compromise in radar stealth. These antennas must, by definition, be efficient at receiving and transmitting electromagnetic signals, the exact opposite property of radar-absorbing materials. Every antenna represents a gap in the stealth coverage where radar energy can penetrate and reflect from internal structures. Advanced designs attempt to hide antennas behind selective frequency surfaces that allow only specific wavelengths to pass, but these compromises never achieve perfect stealth across all radar frequencies. Space-based radar systems present unique challenges for stealth spacecraft. Without atmospheric attenuation, space radars can operate at extremely high frequencies that penetrate many conventional stealth materials. These high-frequency radars can detect surface details and irregularities invisible to lower-frequency systems. The clarity of the space environment also allows for incredibly precise measurement of target characteristics, making even small radar returns potentially sufficient for detection and identification. The degradation of radar-absorbing materials in the space environment creates a maintenance challenge for stealth spacecraft. Continuous exposure to radiation, temperature extremes, and micrometeoroids gradually erodes the effectiveness of these specialized materials. The atomic oxygen present in very low Earth orbits is particularly destructive to many carbon-based RAM coatings. This degradation means that radar stealth performance will inevitably decline over the mission lifetime, with limited options for repair or replacement once deployed. The weight penalty of effective radar stealth is particularly problematic for spacecraft. Launching mass into orbit remains extremely expensive, typically thousands of dollars per kilogram. Effective radar-absorbing materials can add 20 to 30% to a spacecraft's total mass, dramatically increasing launch costs and reducing the payload capacity available for mission equipment. This weight also affects maneuverability, with heavier spacecraft requiring more propellant for orbital changes, propellant that itself adds weight and creates storage challenges. The most effective radar stealth technologies often employ active systems that detect incoming radar waves and generate precisely timed cancellation signals. These systems, known as active cancellation or destructive interference systems, can theoretically reduce radar returns by orders of magnitude beyond what passive materials achieve. However, these systems require significant power, sophisticated electronics, and precise knowledge of incoming radar characteristics. The power consumption and heat generation from these active systems once again increases the spacecraft's infrared signature, trading reduced radar visibility for increased thermal detection risk. Perhaps the most fundamental radar stealth paradox involves the physics of electromagnetic interaction. Any physical object in space must interact with electromagnetic radiation in some way, either reflecting it, absorbing it, or allowing it to pass through. Perfect non-interaction is physically impossible for conventional materials. Even the most advanced metamaterials and engineered surfaces can only manipulate this interaction rather than eliminating it completely. This fundamental physical limitation means that some detectable signature will always exist, regardless of how advanced the stealth technology becomes. The combined challenges of cooling systems and radar invisibility illustrate how spacecraft stealth faces multiple contradictory requirements that cannot be simultaneously optimized. Every solution to one detection risk typically worsens another. This complex interrelationship between different signature types ensures that truly comprehensive stealth, invisibility to all potential detection methods, remains beyond our technological capabilities despite decades of advanced research and development. Beyond these technical challenges of stealth systems, spacecraft designers must confront a completely different category of problems: the logistical and operational hurdles that make stealth spacecraft extraordinarily difficult to deploy and use effectively. These practical considerations often receive less attention than the technological aspects, but they can be equally limiting for real-world applications. A stealth spacecraft requires exceptionally stringent operational protocols that severely restrict its functionality. Standard spacecraft operations involve regular communication with ground controllers, continuous telemetry transmission, active sensor usage, and frequent navigational updates. Stealth operations would require dramatically curtailing or eliminating many of these normal activities. This communication discipline creates significant operational challenges and safety risks for both crewed and uncrewed missions. Communication limitations represent perhaps the most significant operational constraint. A truly stealthy spacecraft would need to minimize or completely avoid radio transmissions that could reveal its position. This creates a one-way information flow where the spacecraft can potentially receive encrypted instructions but cannot confirm receipt or provide status updates without compromising its position. Mission controllers would be operating partially blind, unable to verify that commands were received correctly or that systems are functioning normally. This information gap increases mission risk substantially and makes complex operations nearly impossible to coordinate precisely. For crewed stealth spacecraft, these communication restrictions create psychological challenges as well. Astronauts and cosmonauts rely heavily on regular contact with mission control for both operational and psychological support. Extended periods of communication silence create stress and isolation that can impact crew performance and decision-making. Military submariners undergo extensive psychological screening and training for similar silent operations. But even with this preparation, extended communication blackouts remain challenging for human crews. Supply logistics create another significant operational vulnerability for stealth spacecraft. Any spacecraft requires regular resupply, particularly for crewed missions. But even robotic spacecraft eventually need propellant replenishment or component replacement for extended operations. These resupply missions create predictable patterns of rendezvous that sophisticated surveillance networks can detect and track. Once these patterns are established, observers can predict the approximate location of the stealth spacecraft even without direct observation. The specialized materials required for stealth operations compound these logistical challenges. Many radar-absorbing coatings and thermal control surfaces degrade when exposed to the space environment, particularly atomic oxygen, ultraviolet radiation, and micrometeoroids. These materials require regular inspection and maintenance to maintain their effectiveness. Such maintenance might require spacewalks for crewed vessels or complex robotic operations for uncrewed platforms, activities that significantly increase the risk of detection during the maintenance period. Training requirements for stealth spacecraft operations create additional complexity. Crews must be extensively trained in specialized protocols that differ significantly from standard spacecraft operations. These protocols might include strict emission control procedures, specific attitude management to minimize visibility from predicted observation points, and complex contingency plans for situations where stealth must be temporarily compromised for safety reasons. This specialized training increases preparation costs and limits the pool of qualified personnel for stealth missions. Operational planning for stealth spacecraft requires extraordinarily detailed intelligence about potential observer capabilities and locations. Mission planners need comprehensive knowledge of adversary sensor networks, including orbital parameters of surveillance satellites, capabilities of ground-based tracking stations, and the sensitivity of various detection systems. This intelligence requirement creates its own security vulnerabilities, as the information gathering necessary to plan effective stealth operations might itself reveal interest in specific orbital regions or mission profiles. The operational constraints of stealth create significant opportunity costs as well. A spacecraft operating under strict emission control protocols cannot perform many valuable scientific, commercial, or even military functions that require active sensing or regular communication. This functional limitation means that stealth spacecraft are inherently less versatile than their conventional counterparts, requiring mission planners to make difficult trade-offs between capability and concealment. Emergency procedures present particularly challenging operational dilemmas. Standard spacecraft emergency protocols typically involve increased communication, deployment of visible marker beacons, or even deliberate venting of gases to create visible plumes that aid in rescue operations. A stealth spacecraft in distress faces an impossible choice between maintaining concealment and maximizing survival chances. This fundamental conflict between safety and stealth creates operational risk that cannot be fully mitigated through design or procedure. The time limitations of stealth operation present another practical constraint. While a spacecraft might maintain effective stealth for hours or perhaps days under ideal conditions, extending this concealment to weeks or months becomes exponentially more difficult due to accumulating thermal loads, communication requirements, and maintenance needs. This limited duration restricts the types of missions where stealth capabilities provide meaningful advantages. The combination of these logistical and operational challenges means that even if the technical problems of spacecraft stealth could be solved, which, as we've seen, faces its own nearly insurmountable physics barriers, the practical deployment of such systems would remain extraordinarily difficult. The operational constraints would likely render the spacecraft significantly less effective for most missions compared to conventional designs, raising serious questions about the cost-benefit ratio of stealth spacecraft development. These operational limitations connect directly to another fundamental and perhaps most insurmountable stealth challenge, the impossibility of gravitational concealment. While other detection methods might theoretically be countered with sufficiently advanced technology, gravitational effects remain stubbornly impossible to mask regardless of technological sophistication. Every object with mass creates a gravitational field proportional to that mass. This is a fundamental property of matter that cannot be shielded, absorbed, or redirected with any known or theoretically possible technology. A spacecraft, regardless of its other stealth features, creates a gravitational distortion in space-time that can be detected with sufficiently sensitive instruments. While these gravitational effects are extremely small for spacecraft-sized objects, they are not zero, and detection technology continues to advance rapidly in this field. Modern gravitational observation systems can detect remarkably subtle variations in gravitational fields. The GRACE, Gravity Recovery and Climate Experiment, satellites, for example, can measure changes in Earth's gravitational field sensitive enough to track groundwater movement. Similar technologies, when applied to space surveillance, could potentially detect the gravitational influence of spacecraft at considerable distances. While current systems might not yet have the sensitivity to reliably track individual small spacecraft, the theoretical limit is not technological but relates to instrumentation precision. The movement of a stealth spacecraft creates additional gravitational detection opportunities. As a spacecraft maneuvers through fields of natural space debris or dust particles, it causes tiny perturbations in their trajectories through gravitational interaction. Advanced observation networks monitoring these natural particles can potentially detect these subtle gravitational effects, revealing the presence of an otherwise invisible spacecraft. These indirect detection methods might prove more sensitive than direct gravitational measurement in many scenarios. Microlensing effects represent another gravitational detection avenue that stealth technology cannot address. According to Einstein's theory of general relativity, mass bends light passing nearby, an effect called gravitational lensing. While a spacecraft's mass is too small to create obvious lensing visible to conventional telescopes, extremely precise observations can potentially detect microlensing effects where the spacecraft slightly alters the apparent position or brightness of distant stars as it passes between the observer and the star. These observations require extraordinarily precise astronomical instruments. But the theoretical foundation is sound, and the necessary technology continues to improve. The orbital mechanics of nearby objects provides additional gravitational detection opportunities. A stealth spacecraft in orbit around Earth or another celestial body will slightly influence the orbits of nearby satellites, debris, or natural objects. Over time, precise tracking of these objects might reveal unexplained perturbations that indicate the presence of an otherwise undetected mass. This detection method becomes more effective in densely populated orbital regions where numerous objects can serve as unintentional gravitational sensors. Quantum gravity sensors represent an emerging technology that could further erode possibilities for gravitational concealment. These devices use quantum mechanical principles to achieve unprecedented sensitivity in measuring gravitational fields. Laboratory prototypes have demonstrated the ability to detect tiny mass changes at short distances, and the technology continues to advance rapidly. Future space-based quantum gravity sensors might achieve sensitivity levels that make gravitational concealment of spacecraft effectively impossible, regardless of other stealth measures. Gravitational wave astronomy, while currently focused on massive cosmic events like black hole mergers, establishes principles that could eventually extend to smaller-scale gravitational detection. While a spacecraft would produce gravitational waves far too weak for current detectors, the theoretical lower limits of detection continue to improve as the technology develops. Future gravitational wave observatories might achieve sensitivity levels relevant to spacecraft detection, particularly for larger vessels or those making high-acceleration maneuvers. The fundamental nature of gravity creates a particularly vexing problem because, unlike electromagnetic signatures that can theoretically be absorbed or redirected, gravitational effects cannot be shielded. No known physical principle allows for gravitational insulation or cloaking. Science fiction sometimes imagines gravity shields or similar technology, but these concepts have no basis in our current understanding of physics. According to general relativity, gravity is not a force that can be blocked, but rather a geometric property of space-time itself. Theoretical concepts like negative mass or exotic matter with anti-gravitational properties remain firmly in the realm of speculative physics with no practical implementation path, even if such exotic materials could somehow be created in laboratory conditions. Scaling them to spacecraft applications would present engineering challenges potentially beyond any foreseeable technology. The energy requirements alone for manipulating gravitational fields would likely dwarf the capabilities of any practical spacecraft power system. The impossibility of gravitational concealment represents perhaps the most fundamental limit on spacecraft stealth because it stems from basic physics rather than merely technological limitations. While electromagnetic signatures, thermal emissions, and visual profiles might theoretically be managed with sufficiently advanced technology, the gravitational signature remains an immutable property of the spacecraft's mass. This creates an absolute lower bound on stealth potential. A spacecraft might reduce its other signatures to near undetectable levels, but its gravitational influence remains a potential detection avenue regardless of technological sophistication. This gravitational detection risk, combined with the logistical and operational challenges previously discussed, creates a sobering reality check for stealth spacecraft development. Even if the daunting technical challenges of thermal management, radar absorption, and visual concealment could somehow be overcome, these fundamental physical and practical limitations would still prevent true invisibility in space. The physics of stealth in space remains stubbornly uncooperative regardless of technological advancement. The fundamental physical constraints that make gravitational concealment impossible lead us directly to another critical challenge in stealth spacecraft design: the sustainable energy dilemma. Every spacecraft requires power to function, but generating this power creates multiple signatures that compromise stealth capabilities, regardless of how well other aspects might be concealed. Nuclear power systems, particularly radioisotope thermoelectric generators (RTGS) and small fission reactors, offer the highest energy density for long-duration space missions. However, these systems emit distinctive radiation signatures that are easily detectable at considerable distances. The neutron emissions from fission reactors are particularly problematic for stealth applications, as they can penetrate most shielding materials and travel significant distances through space. Specialized neutron detectors deployed on surveillance satellites can identify these emissions even when other signatures are successfully masked. Even with extensive radiation shielding, nuclear power systems remain detectable. The shielding materials themselves, typically dense metals like lead or depleted uranium, significantly increase the spacecraft's mass, making it more visible to gravitational sensors and requiring more propellant for maneuvers. This shielding also creates a distinctive radar signature due to its high metallic content. Perhaps most problematically, radiation shielding does nothing to hide the intense thermal signature that nuclear power systems inevitably produce as waste heat. Solar power might seem like a more stealth-friendly alternative, eliminating the radiation concerns of nuclear systems. However, solar panels create their own significant stealth complications. Effective solar power requires large panel arrays to capture sufficient sunlight, often spanning dozens of meters for substantial power generation. These enormous reflective surfaces are immediately visible to optical sensors and create distinctive radar returns that can be detected at extreme distances. The geometric arrangement of solar panels is also immediately recognizable as artificial, distinguishing the spacecraft from natural objects like asteroids. The orientation requirements for solar panels further compromise stealth operations. To generate maximum power, panels must be oriented toward the sun, severely constraining the spacecraft's attitude options. This predictable orientation requirement makes the spacecraft's position and movement more predictable to observers. Solar panels also create distinctive thermal patterns, with sun-facing surfaces becoming significantly warmer than shaded components, creating thermal gradients that infrared sensors can easily detect. Battery systems and fuel cells offer temporary alternatives to continuous power generation, potentially allowing for short-duration, silent-running operations. However, these energy storage technologies have fundamentally insufficient energy density for extended spacecraft operations. Even the most advanced lithium-ion batteries store only a fraction of the energy per kilogram that nuclear or solar systems can provide over time. A stealth spacecraft operating solely on batteries might maintain full functionality for hours, or perhaps days, but not the weeks or months required for most meaningful space missions. This limited energy storage creates operational constraints that severely impact mission capabilities. Power-intensive systems like radar, laser communications, and active cooling must be severely restricted or periodically shut down to conserve energy during stealth operations. These restrictions effectively blind the spacecraft and limit its ability to accomplish mission objectives. The choice becomes maintaining stealth at the cost of functionality or maintaining functionality at the cost of stealth, an impossible operational dilemma. The recharging requirements for energy storage systems create another detection vulnerability. Batteries and fuel cells must eventually be recharged using either solar panels or nuclear systems, both of which create significant signatures during operation. This creates a cycle where the spacecraft must periodically compromise its stealth to replenish its energy reserves, providing recurring windows of opportunity for detection. Advanced surveillance networks need only catch the spacecraft during one of these vulnerable recharging periods to begin tracking it continuously. Radioisotope heater units, RHUS, and small radioisotope thermoelectric generators present unique detection challenges. These compact power sources use the natural decay heat from radioactive materials like plutonium-238 to generate small amounts of electricity and heat for spacecraft components. Their relatively low power output makes them inadequate for main spacecraft systems, but useful for keeping critical components warm in the cold of space. However, these devices produce constant thermal and radiation signatures that cannot be turned off or reduced. The radioactive decay continues regardless of operational needs. The cryogenic storage of certain fuels creates additional energy-related detection risks. Liquid hydrogen, often used in high-performance propulsion systems, must be kept at extremely low temperatures to remain liquid. The insulation systems and active cooling required for cryogenic fuel storage consume significant power and create their own thermal signatures. Cryogenic fuels also gradually boil off despite the best insulation, requiring periodic venting that creates visible plumes and detectable material releases. The fundamental thermodynamic inefficiency of all energy conversion systems compounds the stealth energy dilemma. Even the most efficient power systems convert only a portion of their input energy to useful electricity, with the remainder becoming waste heat. Nuclear systems typically achieve 25 to 30% efficiency, meaning 70 to 75% of the energy becomes heat that must be dissipated. Solar panels in space operate at roughly 30% efficiency under ideal conditions. This unavoidable waste heat generation means that power production inevitably creates thermal signatures regardless of the technology employed. The unpredictable space environment creates additional energy management challenges for stealth spacecraft. Solar storms, radiation belt passages, and micrometeoroid impacts can damage power systems or require energy-intensive protective measures. These environmental factors create situations where power consumption might need to increase dramatically and unpredictably, forcing difficult choices between system protection and stealth preservation. The redundancy required for reliable operation in this harsh environment further increases power system complexity, weight, and signature. The sustainable energy dilemma represents one of the most fundamental stealth challenges because it creates a direct conflict between operational capability and concealment. A spacecraft with sufficient power for meaningful military or intelligence missions inevitably generates signatures that compromise its stealth characteristics. This inescapable trade-off means that perfect stealth remains unachievable for any practically useful spacecraft, regardless of technological advancement in other stealth domains. This energy dilemma leads directly to another critical stealth challenge: the vulnerabilities of directional thermal shields. Some spacecraft designers have proposed that while omnidirectional thermal concealment might be impossible, directional shielding could potentially hide a spacecraft's heat signature from specific threat directions. However, these directional approaches create their own set of nearly insurmountable problems that severely limit their practical effectiveness. Directional thermal shields operate on a relatively straightforward principle. concentrating heat emission in specific directions facing away from likely observers. In theory, a spacecraft might appear cold when viewed from Earth if all its heat is radiated in the opposite direction. These systems typically employ highly reflective materials on the Earth-facing side to minimize heat emission in that direction, while high emissivity radiators on the opposite side release accumulated heat into deep space. The most obvious vulnerability of this approach is that it requires precise knowledge of observer locations. In a military context, a stealth spacecraft would need to know exactly where all potential adversary sensors are located to correctly orient its thermal shielding. This might be feasible when hiding from fixed ground stations with known locations, but becomes nearly impossible when considering the dynamic threat environment of mobile sensors, aircraft, ships, and other spacecraft that might host detection systems. Each additional observer at a different angle exponentially increases the difficulty of directional thermal management. The rotation required to maintain proper shield orientation creates detectable patterns that sophisticated tracking systems can identify. Any spacecraft using directional thermal shielding must constantly adjust its attitude to keep the cold side facing potential observers as it moves through its orbit. These regular, predictable rotation patterns differ noticeably from the natural tumbling of space debris or asteroids. Advanced image processing algorithms can identify these distinctive rotational signatures even when the spacecraft itself appears as nothing more than a point of light. Alignment failures in directional shielding create catastrophic vulnerability windows. If the spacecraft's orientation control system experiences even a brief malfunction, the hot side of the spacecraft might temporarily face observers, creating a sudden thermal flare that stands out dramatically against the cold background of space. These momentary exposures might last only seconds or minutes, but advanced persistent surveillance systems continuously monitoring space can detect these brief events and use them to identify and track previously hidden objects. Even with perfect orientation control, heat inevitably builds up within the spacecraft and must eventually be dissipated. The laws of thermodynamics cannot be violated. All the heat generated by onboard systems must ultimately be radiated away. This creates a fundamental operational limitation where the spacecraft can only suppress its thermal signature for limited periods before requiring a cooling cycle that significantly increases detection risk. The longer the mission continues, the more frequently these vulnerable cooling periods become necessary. The physical implementation of effective directional shields creates additional complications. These shields must be substantial structures, often several meters across, to effectively block and redirect thermal radiation. These large shields increase the spacecraft's visual and radar cross-section, potentially making it more detectable in other portions of the electromagnetic spectrum. The shields also add significant mass to the spacecraft, reducing maneuverability and increasing propellant requirements. Directional thermal shields typically employ multiple layers of specialized materials with different reflective and emissive properties. These complex material systems are highly vulnerable to degradation in the space environment. Micrometeoroid impacts can puncture shield layers, creating hotspots visible to infrared sensors. Atomic oxygen in very low Earth orbits gradually erodes many shield materials, reducing their effectiveness over time. Solar radiation, particularly ultraviolet light, breaks down the molecular structure of many specialized coating materials, causing them to lose their carefully engineered thermal properties. The weight penalty of effective directional shielding significantly impacts spacecraft design and capabilities. Thermal engineers estimate that comprehensive directional shielding can add 15 to 25% to a spacecraft's total mass. This substantial weight increase requires larger launch vehicles, more propellant for orbital maneuvers, and reduces the available mass for mission equipment and payload. These compromises directly impact mission capability, creating difficult trade-offs between stealth performance and operational effectiveness. Temperature gradients across the spacecraft create their own detection vulnerabilities, with one side deliberately kept cold while the other runs hot. Heat naturally flows through the spacecraft's structure from hot to cold areas. Managing these temperature gradients requires complex internal insulation systems that add weight and complexity. Despite these measures, some thermal leakage inevitably occurs, creating distinctive temperature patterns across the spacecraft's surface that sophisticated infrared sensors can potentially detect and analyze to determine the craft's overall thermal state. Perhaps most problematically, directional shields are completely ineffective against observers positioned near the spacecraft's hot side. In a contested space environment with multiple potential adversaries, some observation platforms will inevitably have viewing angles that render directional shielding useless. This fundamental geometric limitation means that directional shielding can at best reduce detection probability from specific directions, never eliminate it completely from all possible observation points. Combined with the energy sustainability challenges discussed earlier, these directional thermal shield vulnerabilities further illustrate why truly comprehensive spacecraft stealth remains elusive despite decades of advanced research. Each apparent solution introduces new complications and vulnerabilities that ultimately fail to resolve the fundamental physical constraints that make perfect concealment impossible in the space environment. The fundamental limitations of directional thermal shields point to an even more comprehensive challenge for stealth spacecraft: the problem of multispectral detection. Modern space surveillance systems don't rely on a single detection method, but instead employ multiple sensors operating across different portions of the electromagnetic spectrum simultaneously. This layered approach creates an exponentially more difficult stealth problem that no current technology can fully address. Modern military and intelligence satellites carry sensor packages that can observe targets in visible light, infrared, ultraviolet, dot, and various radar frequencies simultaneously. These multispectral observation capabilities mean that concealment in one portion of the electromagnetic spectrum is insufficient if the spacecraft remains visible in others. A vessel might successfully reduce its radar signature while remaining blindingly obvious in the infrared spectrum, or vice versa. This creates a situation where stealth technologies must address all potential detection methods simultaneously, a dramatically more complex engineering challenge than countering any single detection method. The visible light spectrum represents the most basic detection avenue, where spacecraft appear as moving points of light against the fixed star background. Advanced optical telescopes, both ground-based and space-based, can detect remarkably small objects through direct reflection of sunlight. The International Space Station, for example, is easily visible to the naked eye from Earth's surface despite being hundreds of kilometers away, primarily because of sunlight reflecting from its large solar panels and metallic surfaces. Even much smaller spacecraft create visible signatures when sunlight strikes reflective surfaces at favorable angles. The infrared spectrum presents another detection avenue where spacecraft are particularly vulnerable due to their inevitable heat generation. Infrared sensors can detect temperature differences of fractions of a degree at substantial distances. Military-grade infrared search and track (IRST) systems can detect the heat from spacecraft engines, electronics, and life support systems against the cold background of space from hundreds or even thousands of kilometers away. These systems operate passively, meaning the spacecraft receives no indication that it's being observed, unlike active systems like radar that emit detectable signals. Ultraviolet detection adds another layer to the multispectral challenge. Certain spacecraft components, particularly propulsion systems, emit distinctive ultraviolet signatures during operation. Nuclear reactors produce Cherenkov radiation with characteristic ultraviolet emissions. Solar panel materials interact with ultraviolet light in ways that create distinctive reflection patterns different from natural space objects. Modern surveillance satellites increasingly include ultraviolet sensors specifically to exploit these detection opportunities that might be missed by visible light or infrared systems alone. Radar detection occurs across multiple frequency bands, each with different characteristics and penetration capabilities. Lower frequency radars can detect large objects at extreme distances but provide limited detail. Higher frequency systems offer better resolution but more limited range. Modern space surveillance networks employ multiple radar systems operating across numerous frequency bands simultaneously, making it extraordinarily difficult for spacecraft to implement effective countermeasures across the entire radar spectrum. A stealth technology effective against X-band radar might be completely ineffective against L-band or K-band systems. Radio frequency monitoring creates yet another detection avenue. Every electronic system aboard a spacecraft generates some level of radio frequency emissions, whether from communication systems, radar, computers, or power distribution networks. Specialized signals intelligence satellites can detect and analyze these emissions to identify, locate, and track spacecraft even when they're attempting to maintain radio silence. The characteristic electromagnetic signatures of different equipment types can even allow for identification of specific spacecraft models or classes based solely on their electronic emissions. Nuclear detection represents a particularly difficult multispectral challenge. Spacecraft using nuclear power sources, whether radioisotope thermoelectric generators or true reactors, produce distinctive emissions across multiple portions of the electromagnetic spectrum. Beyond the heat signature, nuclear systems emit gamma radiation, neutrons, and other particles that specialized sensors can detect at significant distances. Neutrino detectors, though still in relatively early development for space surveillance applications, could potentially detect nuclear reactors even through heavy shielding that blocks other forms of radiation. The increasing deployment of hyperspectral sensors further complicates the stealth challenge. Unlike traditional sensors that measure energy in a few broad bands, hyperspectral systems divide the spectrum into hundreds of narrow bands, creating detailed spectral fingerprints of observed objects. These systems can identify specific materials based on their unique spectral absorption and reflection characteristics. The distinctive material composition of spacecraft, aluminum alloys, carbon composites, specialized thermal coatings, creates spectral signatures markedly different from natural space objects, making them identifiable even when other stealth measures are employed. The multispectral detection problem grows exponentially more difficult with each additional sensor type that must be countered. A stealth system addressing 2 detection methods might require, for example, 10 specialized components or materials. Addressing 3 methods might require 30 or more components, with each additional detection method multiplying rather than merely adding to the complexity. This exponential relationship quickly leads to stealth systems so complex that they become impractical to build, maintain, or operate effectively. The power and cooling requirements for multispectral stealth further compound the challenge. Many stealth technologies require significant energy to function effectively. Active radar cancellation systems, adaptive camouflage, and thermal management systems all consume substantial power. This increased energy demand generates additional heat that must be dissipated, potentially making the spacecraft more visible in the infrared spectrum even as it attempts to hide from other detection methods. This creates a vicious cycle where addressing one detection risk often worsens another. The geometric constraints of spacecraft design make simultaneous optimization against multiple detection methods nearly impossible. The shapes that minimize radar reflection often maximize solar reflection. Materials that effectively block infrared emissions typically increase weight, affecting maneuverability and launch costs. Designs that minimize visible detection might compromise communications capabilities. These competing requirements force designers to make significant compromises, resulting in systems that are at best partially effective against the full spectrum of modern detection capabilities. The ongoing advancement of sensor technology consistently outpaces stealth technology development. Each new generation of sensors offers improved sensitivity, wider spectral coverage, and more sophisticated signal processing capabilities. This creates a fundamental asymmetry in the stealth versus detection competition. where defense research must anticipate and counter multiple potential detection advances simultaneously, while detection systems need only succeed through a single method to achieve their objective. This multispectral detection challenge represents perhaps the most comprehensive obstacle to effective spacecraft stealth. While addressing any single detection method presents significant difficulties, the need to simultaneously counter all potential detection avenues across the electromagnetic spectrum creates a complexity barrier that no current or near-future technology can fully overcome. The fundamental physics of how objects interact with electromagnetic radiation in different wavelengths creates boundaries that engineering alone cannot transcend. The multispectral detection challenge leads spacecraft designers to consider an alternative approach to stealth, active countermeasures that confuse or deceive sensors rather than preventing detection entirely. However, these countermeasure systems face their own set of vulnerabilities that severely limit their effectiveness in practical space operations. Traditional electronic warfare countermeasures include technologies like jammers that overwhelm enemy sensors with noise, deception systems that present false targets, and spoofing technologies that manipulate an adversary's perception. While these approaches have proven somewhat effective in atmospheric operations, they face unique challenges in the space environment that dramatically reduce their utility for spacecraft stealth applications. The most fundamental vulnerability of electronic countermeasures is that they must emit energy to function, immediately revealing the spacecraft's presence and approximate location. A jammer powerful enough to overwhelm sophisticated surveillance radars must, by definition, transmit strong electromagnetic signals that other sensors can detect. This creates a self-defeating scenario where the very act of employing countermeasures makes the spacecraft more visible to certain types of sensors. In a multispectral detection environment, this vulnerability becomes particularly problematic, as countermeasures designed to defeat one sensor type often make the spacecraft more visible to others. Power requirements for effective countermeasure systems create additional vulnerabilities. Electronic jammers, in particular, require substantial energy to overcome sophisticated military-grade sensors. This energy consumption generates significant heat that must be dissipated, increasing the spacecraft's infrared signature. The power systems needed to support active countermeasures also add considerable weight to the spacecraft, reducing maneuverability and increasing launch costs. These practical constraints severely limit how long countermeasures can remain active before depleting critical power reserves. Physical countermeasures like decoys and chaff face their own limitations in the space environment. In atmospheric operations, aircraft can deploy chaff, clouds of radar-reflective material, to confuse enemy radars. In space, these materials follow predictable orbital trajectories immediately after deployment that sophisticated tracking algorithms can easily distinguish from actual maneuvering spacecraft. The vacuum of space also prevents these materials from forming the concealing clouds that make them effective in atmosphere. Instead, they quickly disperse into sparse, easily identifiable patterns. Decoy systems designed to mimic the spacecraft's signatures face significant practical challenges as well. To be effective, decoys must accurately reproduce the original spacecraft's radar, infrared, and potentially visual signatures. Creating convincing decoys that match the spacecraft across multiple spectral ranges requires sophisticated technology that approaches the complexity of the spacecraft itself. These complex decoys are expensive, heavy, and consume precious payload capacity that might otherwise be used for mission equipment or additional fuel. The effectiveness of countermeasures diminishes rapidly with repeated use against sophisticated adversaries. The first deployment of a novel electronic warfare technique might successfully confuse enemy sensors, but adaptive signal processing algorithms quickly learn to recognize and filter out these deception attempts. Modern military sensors employ artificial intelligence systems specifically designed to identify and discount electronic countermeasures. This creates a situation where countermeasures provide diminishing returns against capable adversaries, potentially becoming completely ineffective after just a few uses. Timing constraints further limit countermeasure effectiveness. Many electronic warfare systems must be precisely synchronized with enemy sensor operations to function effectively. This requires detailed knowledge of adversary capabilities and operational patterns, information that may be incomplete or inaccurate, particularly against sophisticated military opponents who regularly alter their sensor parameters specifically to defeat countermeasures. Imperfect timing can render even theoretically effective countermeasures completely useless in practical operations. The space and weight requirements of comprehensive countermeasure systems create significant design compromises. Every kilogram devoted to countermeasures represents mass unavailable for mission equipment, propellant, or other critical systems. Modern military spacecraft already face severe constraints on available payload capacity, forcing difficult trade-offs between operational capabilities and defensive systems. These compromises often result in countermeasure systems with limited effectiveness, deployed only against the most likely or dangerous detection threats rather than the full spectrum of potential sensors. Reliability concerns present another significant vulnerability for countermeasure systems. These complex electronic and mechanical systems represent additional potential points of failure in an already challenging space environment. Radiation exposure, thermal cycling, micrometeoroid impacts, and other space hazards can damage sensitive countermeasure components. When countermeasures fail during critical mission phases, the spacecraft may suddenly become vulnerable with no backup concealment options. This reliability risk is particularly concerning for long-duration missions where repair or replacement is impossible. The increasing sophistication of space-based artificial intelligence systems further erodes countermeasure effectiveness. Modern military satellites employ advanced neural networks and other machine learning systems that can identify subtle patterns indicative of deception attempts. These AI systems analyze vast amounts of sensor data across multiple spectral ranges simultaneously, identifying inconsistencies or anomalies that might indicate countermeasure deployment. As these systems continue to advance, their ability to distinguish genuine targets from countermeasures improves exponentially, creating an increasingly unfavorable environment for electronic warfare in space. The legal and diplomatic implications of countermeasure deployment create additional operational constraints. Active jamming of satellite systems could be interpreted as a hostile act under international space law, potentially escalating tensions during sensitive operations. The use of certain types of countermeasures, particularly those that create debris fields or interfere with civilian spacecraft, faces serious legal restrictions. These non-technical constraints further limit the practical utility of countermeasures for many space missions, particularly those operating in crowded orbital regions or during politically sensitive periods. These vulnerabilities collectively demonstrate why countermeasure systems, while potentially useful in specific tactical scenarios, cannot provide comprehensive stealth capabilities for spacecraft. Like other stealth technologies we've examined, countermeasures offer at best partial and temporary concealment rather than true invisibility, the fundamental physics of energy emission in space, combined with the practical constraints of spacecraft design and the relentless advancement of sensor technology, ensures that countermeasures remain a limited and imperfect solution to the spacecraft stealth challenge. The inherent limitations of countermeasure systems have led some aerospace engineers to explore more ambitious concealment technologies. Among the most innovative approaches is active camouflage, systems that actively project images of the background starfield to create the illusion that the spacecraft isn't there. While this concept features prominently in science fiction, the practical implementation faces extraordinary technical limitations that make it largely infeasible for real-world space operations. Active camouflage systems would, in theory, work by covering a spacecraft's surface with advanced display technologies that show what would be visible behind the spacecraft from an observer's perspective. This approach attempts to solve the silhouette problem we discussed earlier, where spacecraft block starlight and create detectable voids in the starfield. However, Implementing this seemingly straightforward concept encounters multiple fundamental physical and technical barriers. The most basic limitation involves the physics of light itself. For perfect camouflage, the system would need to know exactly where every potential observer is located to correctly project the appropriate background image. This becomes an impossible challenge in contested space environments where multiple adversary observation platforms could be monitoring from different angles simultaneously. What appears as perfect camouflage from one observation point would be obviously incorrect from another, potentially making the spacecraft even more conspicuous than if it had no camouflage at all. The light speed delay creates another fundamental physical limitation. Even if a spacecraft could somehow identify the exact position of all observers, the light from stars behind the spacecraft takes time to reach the camouflage system's sensors before it can be analysed and projected forward. This unavoidable delay, though measured in nanoseconds or microseconds, creates a perceptible lag in the projected image that sophisticated observation systems could detect. The faster the spacecraft moves relative to the background and observer, the more noticeable this lag becomes. Energy requirements for effective active camouflage systems are prohibitively high. Creating displays bright enough to match the intensity of stars against the black background of space requires significant power, particularly for larger spacecraft. This energy consumption generates substantial heat that must be dissipated, ironically making the spacecraft more visible in the infrared spectrum while attempting to hide in the visible spectrum. The power systems needed to support active camouflage add considerable mass to the spacecraft, reducing maneuverability and increasing launch costs. The technical limitations of display technologies create additional barriers. Current display systems lack the brightness, resolution, and spectral range necessary to convincingly mimic the star field as seen from multiple viewing angles. Stars vary enormously in brightness, color, dot, and apparent size when viewed through advanced telescopes. Replicating this level of detail across the entire electromagnetic spectrum, not just visible light but also ultraviolet and infrared, exceeds current display technology capabilities by orders of magnitude. Even theoretical future displays would struggle to match the perfect black of space between stars, as all displays emit some level of light, even when showing black pixels. The curvature of spacecraft surfaces presents another significant technical challenge. Most spacecraft have curved or complex geometric shapes rather than flat panels. Projecting undistorted images onto these curved surfaces so they appear correct from multiple viewing angles requires extraordinarily complex optical calculations and display technologies. Current display systems are primarily designed for flat surfaces and perform poorly when bent or curved, creating visible distortions that would immediately reveal the deception. Maintaining perfect camouflage during spacecraft maneuvers becomes virtually impossible. Any change in the spacecraft's position or orientation relative to observers requires instantaneous adjustments to the projected background image. The computational requirements for calculating these adjustments in real time across potentially thousands of display elements exceed current spacecraft computer capabilities. Even minor synchronization errors during maneuvers would create visible artifacts that advanced image processing systems could detect. The space environment itself poses significant challenges for active camouflage technologies. Radiation exposure degrades display performance over time, causing color shifts, dead pixels, and other visible artifacts. Micrometeoroid impacts would damage portions of the display surface, creating permanent visible flaws in the camouflage. Temperature extremes in space, from hundreds of degrees positive in sunlight to hundreds negative in shadow, exceed the operational range of most display technologies, causing failures or performance degradation. Reliability concerns represent another significant limitation. Active camouflage systems would require thousands of coordinated display elements, sensors, and processing systems working in perfect synchronization. This complexity creates numerous potential failure points in an already challenging environment. Unlike passive stealth technologies that often degrade gradually, active camouflage would likely fail catastrophically, switching from apparent invisibility to obvious visibility in an instant if key systems malfunction. This binary failure mode makes active camouflage particularly risky for critical military missions. The weight penalty for comprehensive active camouflage likely makes it impractical for most space applications, covering a spacecraft's entire external surface with high-resolution displays, supporting computers, power systems, and cooling infrastructure could easily double the vehicle's mass. This additional weight dramatically increases launch costs and reduces maneuverability, a particularly problematic trade-off for military spacecraft, where performance often determines mission success or failure. Perhaps most fundamentally, active camouflage systems must themselves interact with electromagnetic radiation to function, precisely what stealth technology attempts to minimize. The sensors required to analyze the background star field must collect incoming light. The displays projecting the camouflage image must emit light outward. These necessary energy interactions create detectable signatures regardless of how sophisticated the camouflage technology becomes. This fundamental physical constraint means that active camouflage, even if technically perfected, would remain vulnerable to appropriately designed counter-stealth sensors. The most advanced theoretical active camouflage systems might combine visual projection with other stealth technologies to address multiple detection methods simultaneously. However, this approach further increases complexity, weight, power requirements, and potential failure points. The engineering challenges of integrating these disparate systems while managing their potentially contradictory requirements exceeds current technological capabilities and may represent a fundamental design barrier rather than merely a temporary technological limitation. These comprehensive limitations explain why, despite its conceptual appeal, active camouflage remains firmly in the realm of science fiction rather than practical spacecraft design. The fundamental physics of light propagation, combined with the harsh realities of the space environment and the practical constraints of spacecraft engineering, create barriers that no foreseeable technology can fully overcome. Like other stealth approaches we've examined, active camouflage might theoretically reduce detection probability under specific, limited circumstances, but cannot provide comprehensive invisibility across all potential observation methods. Beyond the technological limitations of stealth systems themselves, spacecraft face another significant and often overlooked stealth challenge: the problem of space debris interaction. The near-Earth space environment contains millions of pieces of orbital debris, from microscopic paint flecks to defunct satellites the size of automobiles. Any spacecraft moving through this debris field inevitably interacts with it in ways that can reveal its presence regardless of other stealth measures. The most obvious debris-related detection opportunity occurs when micrometeoroid or orbital debris impacts a spacecraft. These impacts, even when caused by tiny particles less than a millimeter in diameter, create brief, intense flashes of light and heat. The kinetic energy of these particles, often traveling at velocities exceeding 10 kilometers per second, converts to thermal energy upon impact, creating momentary temperature spikes thousands of degrees hotter than the spacecraft's normal operating temperature. Advanced infrared surveillance systems specifically designed to monitor space for nuclear detonations or missile launches can detect these impact flashes at considerable distances. Beyond the immediate impact flash, debris collisions create secondary detection signatures. When particles strike spacecraft surfaces, they typically vaporize both themselves and a small portion of the impacted material, creating a microscopic debris cloud that expands outward from the impact point. This debris cloud, though small, interacts differently with sunlight than the background of space, creating subtle but detectable changes in light scattering that sophisticated optical systems can identify. Over time, multiple impacts create distinctive patterns that experienced analysts can recognize as characteristic of artificial rather than natural objects. Stealth spacecraft face a particular challenge with debris management because the specialized materials used for radar absorption and thermal control often perform poorly when subjected to hypervelocity impacts. Radar-absorbing materials typically employ complex, layered structures with precise spacing between components. Micrometeoroid impacts disrupt these carefully engineered structures, creating localized areas where stealth performance degrades significantly. These degraded areas effectively become bright spots to radar systems, potentially revealing spacecraft that would otherwise remain undetected. Thermal control surfaces suffer similar performance degradation when impacted by space debris. The specialized coatings used to manage spacecraft temperature often rely on precisely controlled optical properties that change when damaged. Impact craters create localized hot or cold spots that stand out against the otherwise carefully managed thermal profile of a stealth spacecraft. These thermal anomalies are particularly visible to infrared sensors designed specifically to detect such temperature variations against the cold background of space. The accumulation of space dust on spacecraft surfaces creates another debris-related detection vulnerability. Over time, all spacecraft in Earth orbit collect a thin layer of cosmic dust and human-made particles on their external surfaces. This accumulated material changes the optical and thermal properties of stealth coatings, potentially degrading their performance significantly. The pattern of dust accumulation also differs between natural objects like asteroids and artificial spacecraft, creating another potential recognition feature for sophisticated observation systems. Debris avoidance maneuvers represent perhaps the most significant debris-related stealth challenge. Any spacecraft designed for long-duration missions must include systems to detect and avoid potentially catastrophic collisions with larger debris objects. These detection systems, typically radar or LiDAR-based, must actively emit energy to function effectively, immediately compromising the spacecraft's stealth characteristics when activated. The choice becomes maintaining stealth at the risk of catastrophic collision or preserving the spacecraft at the cost of potential detection, an impossible operational dilemma for critical missions. The pattern of debris avoidance maneuvers themselves can reveal a spacecraft's presence and purpose. Military intelligence analysts carefully monitor known space objects for unexpected maneuvers that might indicate the presence of otherwise undetected spacecraft. The timing, direction, and magnitude of these maneuvers can provide significant insights into a spacecraft's capabilities, mission, and even country of origin. This creates a situation where even successful, undetected debris avoidance reveals valuable intelligence about supposedly hidden spacecraft. Conversely, the absence of expected debris interactions in a specific orbital region can paradoxically indicate the presence of a stealth spacecraft. Space surveillance networks maintain detailed models of debris distribution throughout Earth orbit. Regions where expected micrometeoroid impacts or debris density measurements show anomalous results might indicate the presence of an undetected object absorbing or deflecting the expected particle flux. This shadow detection method becomes more effective as debris monitoring systems become more sensitive and comprehensive. Defensive systems designed to protect spacecraft from debris impacts create additional stealth complications. Whipple shields, layered barriers designed to break up incoming particles before they reach critical spacecraft components, increase the vehicle's size and radar cross-section. More advanced defensive measures like small-scale point defense systems that detect and neutralize approaching debris would require active sensors that emit detectable energy. Electromagnetic shields theoretically capable of deflecting charged particles would generate distinctive magnetic fields detectable at considerable distances. The increasing density of both debris and legitimate spacecraft in valuable orbital regions compounds these detection opportunities. As space becomes more crowded, the probability of close approaches between stealth spacecraft and tracked objects increases significantly. Each such close approach creates opportunities for detection through gravitational perturbation, reflected radar signals, or optical observation during conjunction. This crowding effectively shrinks the available hiding space for stealth spacecraft, regardless of how effective their inherent stealth technology might be. International space debris monitoring networks present a particularly difficult challenge for stealth spacecraft operations. Originally developed for safety purposes, these increasingly sophisticated sensor networks now provide near-continuous surveillance of much of Earth orbit. The combination of radar facilities, optical telescopes, and space-based sensors operated by multiple countries creates a detection mesh difficult to evade completely. Data sharing agreements between countries for debris monitoring purposes mean that even spacecraft successfully evading one nation's sensors might be detected by another's, and the information shared through civilian space safety channels. The space debris challenge highlights a fundamental asymmetry in spacecraft stealth. While detection systems benefit from the combined effects of multiple detection opportunities, stealth systems must successfully address all potential detection methods simultaneously to remain hidden. The interaction between spacecraft and the debris environment creates numerous detection opportunities beyond the traditional electromagnetic signatures we've discussed previously. This asymmetry consistently favors detection over concealment, particularly as both debris populations and monitoring capabilities continue to increase over time. The debris detection challenge, combined with the previously discussed limitations of active camouflage and other stealth technologies, further illustrates why perfect spacecraft stealth remains beyond our current technological capabilities. Each additional physical constraint makes comprehensive stealth exponentially more difficult to achieve, requiring increasingly complex, heavy, and power-hungry systems that ultimately compromise the spacecraft's basic functionality. This accumulation of challenges explains why, despite decades of advanced research, truly stealthy spacecraft remain more theoretical than practical for most space applications. Beyond the numerous technical challenges we've discussed, stealth spacecraft face another critical dimension of difficulty: strategic and practical problems that fundamentally limit their utility even if the technical barriers could somehow be overcome. These strategic considerations often receive less attention than the engineering challenges, but they represent equally important constraints on real-world stealth spacecraft development and deployment. The economics of stealth technology creates perhaps the most immediate strategic limitation: the specialized materials, complex systems, and advanced manufacturing techniques required for effective spacecraft stealth dramatically increase development and construction costs. Military aerospace analysts estimate that stealth features typically increase spacecraft costs by 50 to 100% compared to conventional designs with similar capabilities. This cost premium severely limits how many stealth spacecraft a nation can afford to build and maintain, creating an inherent vulnerability where the loss of even a single vehicle represents a significant strategic and financial blow. This extreme cost drives difficult resource allocation decisions for military planners. Every $1 billion invested in stealth spacecraft represents funding unavailable for other capabilities like improved conventional satellites, ground-based systems, or personnel training. The opportunity cost of stealth technology becomes particularly problematic when considering that even the most advanced stealth systems provide only partial and temporary concealment rather than perfect invisibility. Military decision-makers must weigh whether the limited stealth capabilities justify their extraordinary cost compared to alternatives like deploying larger numbers of conventional spacecraft or investing in counter-space weapons that might neutralize adversary detection capabilities directly. The technological complexity of stealth spacecraft creates significant training and operational challenges as well. Crews and ground controllers require extensive specialized training to maintain the spacecraft's stealth characteristics during operations. This training burden increases personnel costs and limits the available pool of qualified operators. The complexity also extends mission preparation timelines, reducing responsiveness for time-critical missions. These practical limitations mean that even if stealth spacecraft work perfectly from a technical perspective, their operational constraints may significantly reduce their practical utility in real-world military scenarios. The strategic value of stealth diminishes dramatically once adversaries become aware of a stealth spacecraft program's existence, even without detecting specific vehicles. Once potential adversaries know that stealth spacecraft are being deployed, they typically invest heavily in counter-stealth detection systems, improved space surveillance networks, and alternative intelligence collection methods. This creates a situation where the mere knowledge that stealth spacecraft exist drives countermeasure development that may ultimately defeat the original stealth technology, even if specific spacecraft remain temporarily undetected. This acknowledgement penalty creates a paradoxical strategic situation. Nations investing in stealth spacecraft face pressure to acknowledge these capabilities to deter adversaries, but doing so immediately stimulates countermeasure development that reduces the technology's effectiveness. Keeping the capability completely secret preserves technical effectiveness but sacrifices deterrent value. This no-win strategic situation makes stealth spacecraft inherently problematic as long-term strategic assets regardless of their technical performance. Reliability concerns create additional strategic limitations for stealth spacecraft. The complexity of stealth systems introduces numerous potential failure points beyond those of conventional spacecraft. These failures might compromise mission success even if the spacecraft remains undetected. More problematically, certain types of system failures might suddenly reveal a previously hidden spacecraft at the worst possible moment. This catastrophic failure mode creates significant operational risk that limits the types of missions for which stealth spacecraft are suitable. Critical missions with severe consequences of failure typically favor more reliable conventional systems over complex stealth designs, regardless of the detection risk. The limited mission flexibility of stealth spacecraft further restricts their strategic utility. Many valuable space missions inherently require activities that compromise stealth characteristics, communication with ground stations, active sensor operation, or specific orbital parameters that make the spacecraft more easily detectable. A truly stealthy spacecraft might need to avoid these activities entirely, significantly reducing its military or intelligence value. This creates another strategic paradox where the most effective stealth spacecraft might also be the least useful for actual missions. International legal and diplomatic considerations create additional strategic complications. The Outer Space Treaty and related international agreements establish legal frameworks that could potentially be violated by certain stealth spacecraft operations. While the treaties don't explicitly prohibit stealth technology, they do require registration of space objects and promote transparency in space activities. Completely unacknowledged spacecraft operating in disputed areas might violate these principles, creating diplomatic risks beyond the immediate military considerations. These legal ambiguities further complicate the strategic calculus of stealth spacecraft deployment. The interaction between stealth spacecraft and nuclear strategy creates particularly concerning strategic risks. Nations detecting partially observed, unidentified spacecraft near critical nuclear assets might misinterpret them as potential first strike weapons, potentially triggering dangerous escalation during crises. This stabilization risk means that stealth spacecraft, ironically intended to reduce tensions by operating undetected, might actually increase the risk of conflict through misinterpretation or miscalculation during tense international situations. This strategic contradiction further limits the scenarios where stealth spacecraft deployment makes strategic sense regardless of technical performance. The combined weight of these strategic limitations explains why, despite decades of research and substantial investment, truly stealthy spacecraft remain more theoretical than practical in actual military space operations. The extraordinary technical challenges, combined with these fundamental strategic limitations, create a situation where the marginal benefits of partial stealth rarely justify the enormous costs and operational constraints involved. This strategic reality, as much as the technical challenges we've discussed throughout, explains why space remains a domain where hiding is extraordinarily difficult regardless of technological sophistication. These strategic challenges are further compounded by the relentless advancement of detection technologies that consistently erode whatever temporary advantages stealth systems might provide. Future detection capabilities currently in development promise to make spacecraft stealth exponentially more difficult in coming decades, regardless of parallel advances in concealment technology. Quantum sensing represents perhaps the most significant emerging threat to spacecraft stealth. These advanced sensors exploit fundamental quantum mechanical properties to achieve unprecedented sensitivity in detecting subtle signals across multiple portions of the electromagnetic spectrum. Quantum radar systems currently in development could potentially detect stealth spacecraft using entangled photons that reveal the presence of objects without the traditional radar cross-section limitations. These systems could theoretically detect even perfectly radar-absorbing materials by measuring quantum disturbances rather than conventional reflections. Quantum gravimeters, extraordinarily sensitive gravity measuring devices, pose another emerging detection threat. These instruments can detect minute variations in gravitational fields caused by massive objects, potentially revealing the presence of spacecraft regardless of their electromagnetic stealth characteristics. While current quantum gravimeters lack the sensitivity for practical space surveillance applications, the technology is advancing rapidly. Future space-based quantum gravimeter networks could potentially track spacecraft by their gravitational signature alone, a physical property that no stealth technology can eliminate without violating the laws of physics. Distributed aperture systems represent another advancing detection technology that presents significant challenges for stealth spacecraft. Rather than using single large sensors, these systems combine data from multiple small sensors distributed across different platforms or locations. By correlating observations from dozens or even hundreds of sensors, these networks can detect signals far fainter than any individual sensor could perceive. This approach dramatically increases detection range and sensitivity while reducing vulnerability to countermeasures. Future space surveillance networks employing thousands of small, inexpensive satellites with distributed sensing capabilities could make spacecraft stealth practically impossible regardless of technological sophistication. Artificial intelligence and machine learning technologies are revolutionizing how sensor data is processed and interpreted, creating additional detection opportunities. Modern AI systems can identify subtle patterns and anomalies in massive datasets that human analysts would miss entirely. Applied to space surveillance, these systems can correlate data across multiple sensor types, orbital trajectories, and historical observations to identify stealth spacecraft through barely perceptible deviations from expected patterns. As AI capabilities continue to advance exponentially, the ability to process and extract meaningful information from seemingly random data will make concealment increasingly difficult regardless of the physical stealth technology employed. Astronomy networks originally designed for scientific purposes create another emerging detection challenge. The growing global network of ground and space-based telescopes monitoring near-Earth objects, potentially hazardous asteroids, and other astronomical phenomena creates an increasingly comprehensive surveillance network that incidentally monitors much of Earth orbit. Programs like the Legacy Survey of Space and Time, LSST, will soon catalogue virtually every object near Earth down to extremely faint magnitudes. Any stealth spacecraft would need to avoid detection by these powerful astronomical instruments operating outside traditional military surveillance networks and optimized for detecting precisely the kinds of faint, moving objects that stealth spacecraft attempt to mimic. Interferometric astronomy techniques pose a particularly difficult challenge for future stealth spacecraft. By combining observations from multiple telescopes, interferometry can achieve resolution thousands of times greater than individual telescopes. These systems can detect the momentary occultation of background stars as objects pass in front of them, a phenomenon impossible to prevent with any known stealth technology. As interferometric networks become more sensitive and comprehensive, they will increasingly be able to detect spacecraft purely by these unavoidable occultation events, regardless of how effectively the spacecraft might otherwise conceal its electromagnetic signatures. Neutrino detectors represent another exotic but increasingly practical detection technology. Nuclear reactors and certain types of nuclear power systems emit neutrinos, nearly massless subatomic particles that pass through most matter without interacting. While this property makes neutrinos difficult to detect, it also means they cannot be shielded by any known material. Advanced neutrino detectors originally developed for fundamental physics research could potentially identify nuclear-powered spacecraft at significant distances by detecting their neutrino emissions. Unlike other radiation that can be blocked with sufficient shielding, neutrino emissions represent an inevitable signature of nuclear systems that no foreseeable technology can conceal. Dark matter detection technology, while still primarily in the research domain, could eventually create entirely new spacecraft detection capabilities. The extraordinarily sensitive instruments designed to detect faint interactions with theoretical dark matter particles incidentally create systems capable of detecting very subtle disturbances in their local environment. Applied to space surveillance, these hypersensitive detection systems could potentially identify spacecraft through minimal interactions that current technology cannot perceive. The extraordinary sensitivity of these systems, improving with each generation of scientific instruments, creates detection possibilities that current stealth technology cannot address. Persistent surveillance capabilities continue to expand through reduced launch costs and satellite miniaturization. Commercial companies now deploy massive constellations of small satellites for communications and Earth observation, with thousands of platforms providing continuous global coverage. This privatization and democratization of space surveillance creates a detection environment fundamentally different from the limited military systems of previous decades. Future stealth spacecraft would need to evade detection not just from a few specialized military sensors, but from thousands of distributed commercial platforms with increasingly sophisticated capabilities, a dramatically more challenging proposition regardless of stealth technology employed. Perhaps most significantly, the exponential advance in computing power continues to transform detection capabilities across all technologies. Operations that were computationally infeasible a decade ago, like real-time processing of massive multispectral datasets from hundreds of distributed sensors, become routine with each generation of computing advancement. This computational explosion enables increasingly sophisticated signal processing, pattern recognition, and anomaly detection that can extract useful information from seemingly inadequate sensor data. The rapid pace of this computational advancement consistently outpaces stealth technology development, creating an environment where detection capabilities improve more quickly than concealment technologies. The combination of these advancing detection technologies with the fundamental physical constraints and strategic limitations we've discussed throughout this exploration explains why true spacecraft stealth remains extraordinarily difficult despite decades of advanced research and development. While incremental improvements in stealth technology will certainly continue, the fundamental physics of operating in the space environment combined with the relentless advancement of detection capabilities ensures that perfect concealment remains beyond our technological reach, both now and for the foreseeable future. The dream of invisible spacecraft silently traversing the cosmos remains firmly in the realm of science fiction, rather than practical military or civilian space operations.